What if the universe isn't just random events, but a carefully structured system with hidden patterns waiting to be found? New discoveries in cosmology are shedding light on what might have existed before the Big Bang, the event that began everything we know. Join us as we explore these mysteries, question what we thought we knew, and look into the latest discoveries about the universe. As we venture into the mysteries of space, it's essential to keep our own lives organized and secure here on Earth. That's why I'm excited to share Extra with you. They've reimagined the classic wallet, making it smarter, slimmer, and easier to keep track of. Extra recently sent me their latest card holder, and it's as practical as it is beautifully crafted. The card holder is built from space-grade aluminum, making it lightweight yet incredibly durable, and it holds up to 12 cards in a streamlined, slim profile. Plus, it's equipped with RFID blocking technology, providing that extra layer of security against unwanted scans. And with Extra's new solar-powered tracker card, which works seamlessly with Apple's Find My app, you can locate your wallet effortlessly without needing any additional apps. A few hours of sunlight powers the tracker for months, so you'll always know where your essentials are. Right now, Extra is offering a Black Friday sale with up to 50% off, and for the Spacedust community, you can get an additional 5% off by using my code, Spacedust. So, click the link in the description and explore Extra's innovative range and make life a bit simpler and more secure. The question of what existed before the Big Bang is one of the most profound and intriguing in cosmology. The Big Bang marks the birth of our universe, but pondering what came before takes us to the very limits of scientific understanding. One leading theory suggests that the universe may have undergone a series of expansions and contractions, known as the cyclic universe theory. This idea posits that time, as we know it, may have no beginning and no end, with each cycle bringing forth a new universe. Another hypothesis worth mentioning is the concept of a multiverse. This theory suggests that our universe is just one of many that exist within a vast cosmic landscape. Each universe could have its own distinct laws of physics, dimensions, and even origins. In this view, the Big Bang could represent not a singular event in isolation, but rather the moment our specific universe emerged from an overarching multiverse. Additionally, some scientists are exploring the notion that the universe could have originated from a quantum fluctuation in a primordial state. This idea suggests that before the Big Bang, the universe existed in a super-dense primordial form where conventional laws of physics break down. These quantum fluctuations might have created a critical instability, leading to the rapid expansion we now call the Big Bang. While these theories give us exciting possibilities, it's essential to remember that the truth remains elusive. The limits of our current understanding of physics, particularly at the intersection of quantum mechanics and general relativity, make it difficult to answer this foundational question definitively. As our observational technologies advance and theories evolve, we may yet uncover more about the universe's enigmatic beginnings. Modern cosmology has ignited intriguing discussions about the universe's origins, including the concept of a pre-Big Bang universe. Traditionally, the Big Bang theory sets the stage for our understanding of cosmic evolution, describing how our universe expanded from an incredibly hot and dense state approximately 13.8 billion years ago. However, scientists have theorized that the universe's story may extend beyond this singular event. One prevailing idea is rooted in the concept of quantum gravity, which suggests that before the Big Bang, the universe could have existed in a very different state. In this context, the universe may not have started from a point of nothingness, but instead transitioned from a very different realm governed by different physical laws. Some theories propose that our universe emerged from a fluctuating vacuum state or even from a previous contracting universe, hinting at a cycle of birth and rebirth in the cosmos. Furthermore, string theory, a leading candidate for a unified theory of physics, opens up fascinating possibilities regarding the nature of reality before the Big Bang. It posits that our universe is just one of many within a vast multiverse. Each universe in this multiverse could have its own set of physical laws, dimensions, and histories. This idea reshapes our understanding of reality itself, suggesting that the Big Bang was less a beginning and more of a transformation between different states of existence. Finally, Cosmic inflation, the rapid expansion of the universe just after the Big Bang, also plays a crucial role in these discussions. It raises questions about what could have prompted the inflationary phase and what existed prior to it. The profound implications surrounding the pre-Big Bang universe challenge our concepts of time, space, and existence, encouraging us to consider that the universe might have an even richer and more complex narrative than we previously envisioned. Quantum mechanics, the field of physics that describes the behavior of particles at the smallest scales, significantly influences our comprehension of the universe's origins, especially in the moments preceding the Big Bang. Traditionally, our understanding of the universe's early moments relied on classical physics. However, as scientists delved deeper into these extreme conditions, they realized that classical theories fell short. Instead, quantum mechanics emerged as a critical framework for exploring the chaotic and extraordinary environment believed to exist during this period. In the world of quantum mechanics, particles can exist in multiple states simultaneously, a concept often summarized as superposition. This principle could be integral to explaining the conditions just before the Big Bang. Experts theorize that the universe may have originated from a quantum fluctuation within a vacuum state. This idea suggests that even in what seems to be empty space, energy fluctuates, potentially giving rise to the universe we now observe. Such fluctuations could have triggered the rapid expansion of space, commonly referred to as cosmic inflation. Furthermore, quantum mechanics introduces uncertainty, as described by Heisenberg's uncertainty principle. This principle indicates that the precise position and momentum of particles cannot be known simultaneously. In the context of the early universe, this uncertainty could imply a chaotic mixture of particle types and energies, paving the way for the rich tapestry of matter and energy that would eventually lead to the formation of stars, galaxies, and planets. The seemingly random nature of quantum events could provide insight into the initial conditions that set the stage for our universe. As we explore these ideas, one of the most intriguing implications is the concept of the multiverse. Some interpretations of quantum mechanics suggest the existence of multiple, perhaps infinite universes with varying properties and dimensions. This perspective challenges our singular understanding of the cosmos and invites us to contemplate what lay beyond the Big Bang. Ultimately, quantum mechanics not only acts as a bridge to comprehend our universe's inception, but also urges us to rethink the very fabric of reality itself. The concept of singularity is a fascinating aspect of cosmology, particularly when we consider the events that preceded the Big Bang. In simplest terms, a singularity represents a point in space where certain quantities, like density and temperature, become infinite. Within the framework of our universe, this idea suggests that before the Big Bang, all matter and energy were concentrated into a singularity, creating immense gravitational forces and leading to the conditions necessary for the event itself. As we look back in time towards the origins of the universe, things become increasingly complex. The Big Bang theory posits that the universe began expanding from this singular state approximately 13.8 billion years ago. But what exactly happened at that moment? Understanding singularity invites profound questions about the nature of time and space. While time, as we perceive it, began at the moment of the Big Bang, the idea of before becomes a tricky proposition. According to our best models, time may have emerged from the singularity itself, suggesting that there is no before in a conventional sense. Moreover, theoretical physics has proposed various models to explain what might have happened before this monumental event. One possibility suggests that the universe could have gone through a cycle of expansion and contraction, hinting at a multiversal scenario where singularities can mark entrances into different regions of time and space. Another intriguing perspective involves quantum fluctuations, which imply that the very fabric of spacetime might have experienced chaotic behaviors leading up to the Big Bang, potentially resulting in the birth of our universe. Though these ideas remain speculative, they inspire continued exploration into the complexities of existence itself. Singularities challenge our understanding of the cosmos and the laws of physics as we know them. They compel us to think deeply about the origins of everything we observe today. As scientists develop new technologies and methods to probe the universe's early moments, the mystery of what lies beyond that singularity continues to fuel scientific inquiry and philosophical contemplation alike. Physicists often turn to mathematical models as essential tools for exploring the mysterious conditions that may have existed prior to the Big Bang. These models allow scientists to delve into concepts that go beyond direct physical observation, making it possible to form hypotheses about a time when the universe was vastly different from what we know today. The pre-Big Bang era is characterized by extreme conditions and unique states of matter and energy, which can be puzzling to comprehend without these abstract tools. One prominent example is string theory, which proposes that fundamental particles are not merely point-like objects, but rather tiny, vibrating strands of energy. In this framework, physicists craft intricate mathematical formulations to analyze how these strings could behave in environments where traditional laws of physics might not apply. This approach provides a way to suggest what matter and forces might have interacted like before the universe began to expand, offering insights into the very fabric of reality. Another significant area of research involves the concept of quantum gravity, attempting to unify general relativity and quantum mechanics. Models that incorporate elements of both theories enable physicists to investigate how gravity might function at singularities, such as those believed to exist at the beginning of the universe. These models reveal how space and time could behave differently in extreme conditions, suggesting that our understanding of these concepts may need radical revision when considering the universe's earliest moments. Lastly, cosmological simulations use powerful mathematics to create virtual universes, allowing scientists to examine how various initial conditions could lead to the universe we observe today. By tweaking parameters and observing the results, physicists can gain insights into potential scenarios of cosmic evolution, including those that might have characterized the pre-Big Bang epoch. This blend of mathematics and cosmology enriches our understanding and keeps the quest for knowledge alive in the ever-expanding realm of the universe's history. In the context of pre-Big Bang conditions, scientists grapple with the very concept of time itself. Traditionally, time is understood as a measure of change, seconds ticking by, events unfolding in a sequence. However, before the Big Bang, that familiar notion of time begins to unravel. The prevailing theories suggest that time as we know it did not exist in the conventional sense. Instead, it was bound up with processes that we still struggle to fully comprehend. To delve deeper, it's crucial to consider the nature of the universe before the Big Bang. Some researchers propose that at this point, the universe was compressed into an incredibly hot and dense state. In this scenario, the attributes of space and time were intertwined, forming what we call spacetime. This means that without the universe as we perceive it today, expanding and cooling, there may have been no time. The emergence of time could very well be linked to the moment when the universe began to expand, marking the beginning of both space and temporal order. Furthermore, scientists explore concepts like quantum gravity to understand these early conditions. These theories suggest that the conventional framework of time breaks down at quantum scales. Instead of moving through the fabric of time in a linear fashion, the dynamics of the early universe could involve a more complex interplay of events that don't align with our typical understanding of past, present, or future. This opens up fascinating ideas about time being a property that emerged with the universe itself. Ultimately, the exploration of time in the pre-Big Bang context challenges us to rethink not just the nature of time, but also our place in the cosmos. As scientists continue to investigate these mysteries, they push the boundaries of our knowledge, inviting us to contemplate the very essence of existence and the universe's beginnings. Each insight adds a layer to our understanding of how everything, space, time, and life, interconnects in this vast tapestry we call reality. The Planck era is a critical period in the history of our universe, marking the very beginning of time and space as we understand them. This era lasted from 0 seconds to about 10 to the negative 43 seconds after the Big Bang. During this minuscule fraction of time, the universe was unimaginably small, hot, and dense. The laws of physics as we know them break down under such extreme conditions, making the Planck era a frontier of scientific exploration and speculation. Understanding the Planck era helps scientists delve into the fundamental forces of nature. At this time, gravitational, electromagnetic, and nuclear forces were indistinguishable due to the extreme energy levels present. This suggests that these forces may have originated from a single, unified force. By investigating this early stage of the universe, researchers hope to uncover insights into how these forces separated and evolved into the fundamental interactions we observe today. This focus on the Planck era also raises profound questions about the nature of the universe. Questions arise about what existed before the Big Bang and what initiated this explosive expansion. Theoretical physicists employ models rooted in quantum mechanics and general relativity, trying to piece together a coherent narrative of our universe's origins. Concepts such as quantum gravity are vital in these discussions, as they aim to bridge the gap between particle physics and cosmology. As we explore the mysteries of the Planck era, we encounter more than just scientific inquiry. We delve into the essence of existence itself. This period invites us to consider our place in the universe, encouraging a deeper understanding of the cosmos's birth and development. Ultimately, the significance of the Planck era lies not only in what it reveals about the early universe, but also in how it challenges our perceptions of reality and the very fabric of time and space. The concept of the Big Bang is often viewed as the very beginning of both space and time. However, recent theories exploring pre-Big Bang events introduce a provocative notion that the cosmos may have existed in some form even before this monumental event. This challenges the traditional view by suggesting that both space and time are far more elastic and complex than once imagined. Instead of a singular starting point, it opens the door to various interpretations of how the universe might have been structured or how it could have functioned prior to that first spark. One intriguing area of research delves into the idea of a cyclic universe. In this model, the universe undergoes infinite cycles of expansion and collapse. Each Big Bang is not the absolute beginning, but rather a transition point from a previous state. This posits that instead of a linear progression, time may be more like a circular path, leading to the possibility that events preceding each Big Bang could influence subsequent ones. This perspective fundamentally alters how we think about causality, as actions taken in one cycle could echo into the next. Another interesting line of inquiry involves quantum mechanics and the nature of reality itself. Some physicists theorize that before the Big Bang, the universe may have existed in a state governed by quantum fluctuations, where the very concepts of space and time as we understand them were not yet applicable. In this realm, particles could be both here and there all at once. This notion challenges the classical understanding that our universe operates under fixed laws of time and space, suggesting instead that reality at its most fundamental level may be inherently unpredictable and interconnected. These theories are not just academic musings. They invite us to rethink what we know about existence itself. If the universe is indeed a tapestry woven through both time and space that extends far beyond the Big Bang, the implications stretch into the very fabric of how we perceive our reality. They urge us to embrace the mysteries that lie beyond traditional cosmological ideas and consider that what we label as beginnings and endings might be moments in an ongoing and magnificent story of cosmic evolution. The concept of time as we understand it has deep connections to the birth of the universe itself, particularly with the event known as the Big Bang. Deep within the scientific community, there is a compelling argument that time, in its familiar form, may not have existed prior to this crucial moment. To unpack this idea, we need to look at both theoretical implications and empirical evidence that supports it. According to our current understanding of physics, particularly the theory of relativity, time is interwoven with space to form what we refer to as spacetime. Before the Big Bang, it is believed that the universe was in an incredibly hot and dense state where the very fabric of spacetime emerged. In this context, any discussion of before the Big Bang becomes problematic, as time itself may not have had a framework in which to exist. Thus, the Big Bang represents not just a dramatic expansion of the universe, but also the inception of time itself. Further bolstering this idea are models stemming from quantum gravity and string theory, which suggest that at the fundamental level, the universe might behave quite differently than our everyday experiences lead us to expect. These models propose scenarios where concepts of time break down. In a way, this mirrors the notion of the singularity that marks the Big Bang, a point where our conventional understanding of physics ceases to apply. Additionally, observational evidence, such as the cosmic microwave background radiation, reinforces the idea that our universe had a tangible beginning marked by the Big Bang. This remnant radiation is a snapshot of the early universe, providing clues about the conditions that existed shortly after its inception and suggesting a definite point in time from which all subsequent moments flow. Therefore, while the question of what existed before the Big Bang may seem intuitive, current scientific perspectives indicate that our very notion of time itself may have been born along with the universe. The concept of spacetime, as we understand it today, undergoes a fascinating transformation when we delve into the pre-Big Bang universe. Traditionally, we think of spacetime as a fabric that intertwines the three dimensions of space with time itself. However, the conditions before the Big Bang challenge this understanding profoundly. Before the event that initiated our universe, it's hypothesized that spacetime as we know it did not even exist in a recognizable form, making discussions around it both intriguing and complicated. In the moments leading up to the Big Bang, many scientists suggest that the universe was in an extremely hot, dense state. This singularity, in which temperature and density tend toward infinity, poses questions to our existing models of physics. The mathematics of general relativity break down in such extreme conditions, indicating that our conventional understanding of spacetime fails. Instead of a structured timeline that unfolds within an established spatial context, we might have to reconsider the very fabric that holds time and space together. Theories such as quantum gravity explore the very nature of spacetime at these extraordinary scales. Some propose that spacetime may be more fluid and dynamic than we realize, potentially stretching or warping in ways that we have yet to comprehend. In this context, spacetime could have been in a state of potentiality, not quite developed as we experience it today. Thus, the evolution of spacetime becomes intricately linked to processes that led to the creation of our universe, presenting a canvas of possibility before our reality took form. As we continue to explore these concepts, it's becoming increasingly evident that the narrative of the pre-Big Bang universe may shift our fundamental understanding of physics altogether. With more advanced theories and potential discoveries awaiting us, the mystery of what existed before spacetime adds yet another layer of intrigue to the ongoing journey of unraveling the universe's deepest secrets. Scientists are embarking on a quest not just to find answers, but to reshape the very questions we ask about existence itself. The Cyclic model presents a fascinating perspective on the nature of time and space, proposing that our universe undergoes endless cycles of expansion and contraction. According to this view, instead of a singular beginning like the Big Bang, the universe experiences a series of these cosmic events. After reaching a point of maximum expansion, the universe, instead of fading into nothingness, contracts back to a state of incredibly high density, ultimately leading to another Big Bang. This cyclical process suggests that time and space are not finite, but are perpetually renewed. One of the most intriguing implications of this model is the idea of continuity. It challenges the traditional notion of a defined beginning and end, suggesting that time may be infinite in a sense that it continually unfolds across these cycles. Each cycle could represent a unique iteration of the universe, potentially evolving with different physical properties or laws. This viewpoint leads to philosophical questions about the nature of existence and reality as we know it, suggesting that our current understanding of time might be just one chapter in an endless story. Moreover, the cyclic model posits that the universe could preserve certain features or structures over these cycles, such as the patterns of cosmic background radiation and the distribution of galaxies. This accumulation of cosmic memory hints at a deeper interplay between the past and the future, where each cycle informs the next. Essentially, it offers a vision where the universe is seen as a dynamic, ever-repeating tapestry, woven together by the threads of time and space. The cyclic model invites us to reconsider fundamental concepts of time and space. Instead of a linear progression from the Big Bang to a finale, it suggests a rhythmic dance of cosmic evolution that is both eternal and transformative. This perspective not only reshapes our understanding of cosmology, but also sparks intriguing considerations about the destiny of our universe and the nature of reality itself. Cosmic inflation theory revolutionizes our understanding of the universe's infancy by proposing a dramatic expansion of space during the first moments after the Big Bang. This theory suggests that within a fraction of a second, the universe expanded exponentially, growing from smaller than an atom to the size of a solar system. This incredibly rapid expansion smooths out any irregularities, leading to the uniformity we observe in the cosmic microwave background radiation today. Before inflation was proposed, the Big Bang model could not fully explain the vastness and homogeneity of the universe. Cosmic inflation provides a framework for understanding how our universe transitioned from an incredibly dense and hot state into the cooler, expanding cosmos we see now. It bridges the gap between quantum physics and cosmology, suggesting that quantum fluctuations during inflation could be the seeds of all the large-scale structures we observe, like galaxies and clusters. Moreover, this theory opens up intriguing possibilities about what might have existed before the Big Bang, with some researchers proposing that our universe could be one of many in a multiverse, a concept where an infinite number of universes exist, each with different properties. These ideas challenge our traditional notions of time and space, suggesting that the fabric of reality may be woven with threads of potential realities. By exploring cosmic inflation, scientists gain deeper insights into the fundamental laws governing the universe and the history of its creation. This perspective not only enriches our understanding of the universe's early moments, but also encourages further research into the nature of existence itself, continually feeding our curiosity about what came before the seemingly inconceivable moment we call the Big Bang. Cosmic inflation is a groundbreaking theory that reshapes our understanding of the universe's beginnings. This concept suggests that shortly after the Big Bang, the universe experienced a rapid expansion, growing exponentially in size within fractions of a second. This period of inflation could have implications for what happened before the Big Bang, raising fascinating questions about the nature of the cosmos. Before the advent of cosmic inflation, many scientists assumed the universe started in a hot, dense state with no prior history. However, inflation introduces the possibility that our universe is just a small part of a much larger multiverse. This multiverse concept proposes that other regions of space could exist beyond our observable universe, potentially leading to different laws of physics. This radical idea expands our thinking about what the universe could be and suggests that multiple Big Bang events may have occurred in this grand cosmic landscape. One of the most intriguing aspects of inflation is its ability to solve several enigmas of the Big Bang theory. For instance, it addresses the uniformity of the cosmic microwave background radiation. This radiation is remarkably consistent across vast distances, despite the observable universe being filled with variations. Inflation proposes that the universe was once in a state of near-perfect uniformity, which was then stretched to the size of the observable universe, leaving behind this smooth background. Additionally, cosmic inflation impacts our understanding of the structure of the universe. It suggests that tiny fluctuations during this rapid expansion serve as the seeds for galaxies and large-scale structures we observe today. As inflationary periods influence the distribution of matter, they weave the intricate tapestry of the cosmos we continue to explore. Thus, cosmic inflation not only deepens our understanding of the Big Bang, but also invites us to reconsider the nature and origins of everything we see in our universe. Scientists employ a variety of innovative methods to test the validity of inflationary models, which explain the rapid expansion of the universe just after the Big Bang. One of the primary approaches involves the analysis of the cosmic microwave background, or CMB. This relic radiation from the early universe serves as a snapshot of the cosmos when it was just a mere fraction of a second old. By examining tiny fluctuations in temperature and density in the CMB, scientists can infer details about the physics of inflation, including its duration and the energy scale involved. In addition to the CMB, researchers also look for specific patterns of gravitational waves, which are ripples in spacetime caused by accelerating masses. Inflationary models predict that such waves should exist and that their signatures can be faintly detected. By utilizing advanced instruments like the Laser Interferometer Gravitational Wave Observatory, scientists are on the lookout for these gravitational signatures that would provide strong evidence supporting inflationary theory. Furthermore, scientists conduct simulations of large-scale structure formation in the universe. These simulations help them observe how galaxies and cosmic structures would evolve under different inflationary scenarios. By comparing the predicted distributions of galaxies and clusters to those observed in surveys, researchers can assess the accuracy of various inflationary models. A match between simulation and observation can lend significant weight to a given model of inflation. In recent years, new observational missions, such as the Planck satellite, have greatly enhanced our understanding by providing high-resolution maps of the CMB. As data continues to accumulate, our comprehension of the early universe deepens, bringing with it a remarkable glimpse into how inflation might have shaped our reality. Through this multifaceted approach, scientists are working tirelessly to validate and refine the intricate theories surrounding the universe's explosive beginnings. Inflationary theories play a crucial role in understanding the large-scale structure of the universe. At the core of these theories lies the concept that, during the very early moments after the Big Bang, the universe underwent an exponential expansion. This rapid stretching of space helped to resolve some of the significant challenges posed by the observed uniformity and smoothness of the cosmos, particularly the principles of homogeneity and isotropy. Homogeneity refers to the idea that the universe looks the same at every point when viewed on a large scale. Isotropy means that the universe appears the same in all directions. These properties are evident in the cosmic microwave background radiation, where tiny fluctuations exist but are remarkably uniform when viewed at a grand scale. Multiverse theories offer intriguing perspectives on what might have existed before the Big Bang, challenging our traditional understanding of the universe's origin. According to these theories, our universe is just one of many, possibly an infinite number, existing alongside each other in a vast multiverse. This idea opens up a realm of possibilities about the state of reality before the explosive event that gave rise to space and time as we know it. One prominent concept within multiverse theories is the idea that different universes may arise from various physical laws or conditions. This means that while our universe is characterized by specific constants and properties, there could be universes with entirely different characteristics. Some models suggest these universes might have emerged from a parent universe, undergoing a process of cosmic inflation or transformations that created branching realities. In this scenario, rather than a singular beginning, the multiverse frames existence as a dynamic interplay of many beginnings, some of which may precede our own. Moreover, certain theoretical frameworks propose that time itself might not have always existed as we understand it. Before the Big Bang, in this view, there could be a state of existence that is timeless or characterized by entirely different dimensions. For instance, some physicists suggest the possibility of a cyclical universe where the Big Bang is simply one transition in an endless series of expansions and contractions. This perspective allows for the consideration that prior states or forms of reality existed independent of our traditional notions of beginning and end. As scientific understanding evolves, multiverse theories challenge us to rethink our universe's origins and raise profound philosophical questions about existence. They inspire both awe and curiosity, moving our inquiries beyond the singular event of the Big Bang to a broader landscape of cosmic possibilities. In this vast expanse, the boundaries of our understanding stretch and shift, inviting us to explore not just what exists within our universe, but the nature of reality itself across potentially limitless dimensions. The concept of the multiverse opens up a fascinating array of ideas, especially when we delve into pre-Big Bang scenarios. One prominent theory suggests that rather than being a singular event, our universe is just one of many that have emerged from an infinite sea of other universes. This idea can be traced back to the inflationary model of the early universe, which posits that rapid expansion occurred shortly after the Big Bang. According to this view, different regions of space underwent inflation in varying ways. leading to pockets of space that became distinct universes, each with its own unique properties. Another intriguing multiverse theory is the cyclic model. This hypothesis proposes that our universe undergoes endless cycles of expansion and contraction. In this scenario, each cycle ends with a big crunch, followed by a new Big Bang, giving rise to a new universe. This continual rebirth offers a rich tapestry of possibilities and allows for the exit of various physical laws and constants that could differ across cycles, resulting in a vast multiverse landscape where each universe has its own distinct characteristics. The landscape multiverse further expands these ideas. It arises from string theory, which suggests that fundamental particles are made up of tiny vibrating strings. String theory allows for a multitude of ways these strings can vibrate, each leading to different physical laws and universes. Within this framework, there are potentially 10,000 or even more unique combinations that describe different versions of reality. Some of these universes may have conditions that allow for life, while others might operate under completely alien physical laws. Lastly, we have the concept of the quantum multiverse, which springs from quantum mechanics. In this view, every time a quantum event can have multiple outcomes, the universe splits into different branches, with each outcome occurring in its own universe. This means countless versions of reality coexist, mirroring the scenarios in which all possible outcomes play out. When considering pre-Big Bang scenarios, these theories invoke the idea that even before our universe came into being, there might have been a wide array of alternate existences already unfolding. Each of these multiverse theories offers a unique lens through which to explore our cosmic origins, reminding us of the vast interconnected possibilities of existence. The concept of the multiverse is one of the most tantalizing ideas in modern cosmology. It suggests that our universe, with its vast galaxies, stars, and planets, might be just one of many universes existing simultaneously. This possibility stems from various theoretical frameworks, primarily stemming from quantum mechanics and cosmic inflation. Scientists have long sought to understand why our universe has the specific conditions that allow life. The multiverse theory offers a compelling explanation. If many universes exist, it is not surprising that at least one of them would have the right conditions for life. One of the key ideas supporting the multiverse hypothesis comes from cosmic inflation, a theory that describes the rapid expansion of the universe just after the Big Bang. This inflationary phase suggests that different regions of space could have expanded differently, leading to pocket universes that have distinct properties. These bubble universes could have varying laws of physics, constants, and dimensions, resulting in a remarkable diversity of universes, some of which could support life and others that are utterly uninhabitable. Another angle comes from quantum mechanics. The many worlds interpretation postulates that every quantum event creates a branching of the universe into multiple realities, where every possible outcome is realized in its own separate universe. This interpretation challenges the classical view of a single reality, opening up the realm of possibilities that there are countless universes, all arising from the fundamental principles of quantum physics. While the multiverse remains a speculative idea and presents significant challenges in terms of empirical testing, it inspires scientists and enthusiasts alike. It challenges our understanding of existence itself and raises profound questions about the nature of reality. As researchers continue to explore the cosmos, the notion of our universe being part of a vast multiverse keeps us questioning and pondering what else might be out there beyond the observable limits of space and time. The concept of a multiverse suggests that our universe is just one of many that exist, potentially with different laws of physics and constants. While the idea may sound like something from science fiction, intriguing evidence could hint at the existence of multiple universes, even before the Big Bang. One significant piece of evidence comes from the phenomenon of cosmic inflation. This theory proposes that just after the Big Bang, the universe underwent an exponential expansion. Some scientists speculate that this inflationary process could occur repeatedly, generating bubbles that become separate universes. The remnants of such inflation might leave behind patterns in the cosmic microwave background, the faint glow left over from the Big Bang. If we could identify anomalies or unusual patterns that cannot be explained by standard cosmology, it could suggest interactions with other universes. Further support for the multiverse idea stems from string theory, which posits that the fundamental building blocks of the universe are not point-like particles, but rather tiny, vibrating strings. This framework allows for enormous variations in physical laws, meaning our universe's properties could be just one of countless outcomes in a vast landscape of possibilities. The mathematical framework underlying string theory produces models with many dimensions and variations, potentially creating an environment where different universes could coexist. Context from quantum mechanics also fuels the multiverse hypothesis. The theory of quantum mechanics suggests that particles do not have definite states until measured. This has led to interpretations that propose entire realities branch out with every quantum event, leading to an infinite number of parallel worlds. While speculative, this idea resonates with the notion that universes could emerge from decisions or events that happen at the cosmic scale, extending the timeline of existence back to a period before the Big Bang itself. While concrete evidence for a multiverse remains elusive, theories like cosmic inflation, string theory, and quantum mechanics provide tantalizing possibilities that could illuminate the existence of multiple universes, possibly even prior to our own universe that we recognize today. The concept of a multiverse presents a fascinating framework for understanding the origins of our universe and its early moments. Traditionally, many have pondered the question of how our universe began, often leading to the idea of a singular Big Bang event. In contrast, the multiverse theory suggests that what we perceive as our universe may be just one of many, each emerging under its own distinct conditions. This perspective challenges the notion of a singular beginning, inviting us to consider multiple cosmic histories. In this multiverse scenario, universes can vary dramatically in their physical laws, constants, and even dimensions. Some may emerge from the remnants of previous universes that collapsed, while others could manifest from quantum fluctuations in a more significant cosmic landscape. This means that the beginning of our universe might not be a unique event, but rather part of an ongoing cycle of creation, expansion, and potential rebirth within a broader multiversal framework. Furthermore, the multiverse concept can help to address some of the perplexing features of our own universe, such as its remarkable fine-tuning for life. With an infinite or vast collection of universes, each with different properties, it becomes less surprising that at least one universe, like ours, would develop conditions conducive to life. In this light, rather than being an anomaly, our universe could be just one of countless realms, each representing a different outcome in the cosmic lottery. As we delve deeper into these ideas, the multiverse not only enriches our understanding of cosmic origins, but also ignites our curiosity about existence itself. It pushes the boundaries of traditional cosmology, inspiring scientists and thinkers to explore the fundamental questions of reality, existence, and the nature of the cosmos on a grand scale. This entanglement of possibilities challenges our definitions of beginning and universe, leading us to contemplate an infinite tapestry of realities, each with its own story to tell. Quantum gravity is a fascinating area of theoretical physics that seeks to merge the principles of quantum mechanics with the force of gravity. This effort becomes particularly intriguing when we consider frameworks that describe a pre-Big Bang universe. Quantum gravity suggests that at the smallest scales, the fabric of spacetime is not smooth and continuous, but rather discrete and subject to the uncertainty dictated by quantum mechanics. In models of a pre-Big Bang scenario, quantum gravity plays a critical role in understanding what might have existed before our universe began to expand nearly 14 billion years ago. Traditional theories of gravity, grounded in general relativity, break down under extreme conditions, such as those thought to exist at the very beginning of time. Quantum gravity proposes that all particles and forces, including gravity, manifest through a fundamental quantum field. This allows for the possibility that the universe could have undergone a different phase or state before the Big Bang, rather than being an absolute beginning. Some models, like the Cyclic universe scenario, incorporate elements of quantum gravity to suggest that the universe goes through infinite cycles of expansion and contraction. In this view, the Big Bang is not a singular event, but rather a transitional phase. The quantum fluctuations during this contraction could lead to a new Big Bang, allowing for a continuous series of cosmic rebirths. Such considerations challenge our conventional notions of time and space, inviting us to think about the universe in a way that defies simple linear progression. Moreover, quantum gravity may offer insights into some of the fundamental properties of the universe. For example, the concepts of entropy and causality take on new dimensions in a pre-Big Bang context. Understanding how spacetime behaves at these quantum levels could reveal deep connections to the laws governing the universe, emphasizing the interplay between the microscopic and the cosmic. As we delve deeper into this realm of theoretical physics, we are continually reminded of how much remains to be discovered about the origins of our universe and the profound complexities underlying its existence. String theory is a captivating framework in theoretical physics that aims to reconcile quantum mechanics and general relativity. Its implications extend beyond our observable universe, sparking intriguing possibilities about conditions and realities that may have existed prior to the Big Bang. Essentially, string theory posits that the fundamental building blocks of the universe are not point-like particles, but rather tiny vibrating strings of energy. These strings can exist in multiple dimensions, some of which remain beyond our everyday experience. In the context of the universe before the Big Bang, string theory introduces the concept of a pre-Big Bang scenario. It suggests that the structures of space and time may have undergone significant transformations, having originated from a state of higher dimensional space known as the string landscape. In this model, the fluctuations and interactions of strings could have paved the way for the rapid expansion that we recognize as the Big Bang. This thinking challenges traditional ideas, proposing that our universe might be just one of many phases within a more extensive and complex multiverse. Moreover, string theory allows scientists to consider how the laws of physics themselves may have been different in the very early universe, or even non-existent as we define them today. In this framework, the forces and particles that define our realities could emerge from the dynamics of strings interacting in higher dimensional spaces. This opens up avenues to explore what time could have meant in a pre-Big Bang universe and how our understanding of causality might need to evolve. While the specifics of the universe before the Big Bang remain largely speculative, string theory offers a tantalizing glimpse into potential origins and an underlying unity in the cosmos. By examining these ideas, scientists hope to unravel the mysteries that lie at the edges of our understanding, pushing the boundaries of what we know about the universe's history and the fundamental nature of reality itself. String theory, a leading candidate in the search for a unified theory of physics, presents revolutionary ideas that significantly challenge our traditional cosmological concepts. At its core, string theory posits that the fundamental building blocks of the universe are not point-like particles, but rather tiny, vibrating strings. These strings can oscillate in various ways, giving rise to the different types of particles we observe. This concept not only alters our understanding of particle physics, but also leads to profound implications for the structure of the cosmos itself. One major challenge posed by string theory is the idea of extra dimensions. While traditional cosmology typically operates within the familiar 3 dimensions of space and one of time, string theory suggests that there are additional dimensions, potentially as many as 10 or 11. These extra dimensions are compact and not directly observable at the everyday scale. However, their implications ripple through the fabric of space and time, influencing the fundamental forces and the way gravity operates, potentially explaining phenomena that standard models cannot adequately address. Moreover, string theory introduces the notion of a multiverse, a collection of multiple, possibly infinite universes, each with its own unique laws of physics. This challenges the traditional perspective that our universe is the only one that exists. Instead, it opens the door to a vast array of possibilities where different universes may have different constants and fundamental forces. Such a radical shift encourages cosmologists to explore the implications of how our universe fits into this broader multiverse framework, raising questions about the nature of reality itself. Lastly, the mathematical complexities inherent in string theory often lead to a more speculative approach to cosmology. While traditional models may focus on observable phenomena and empirical data, string theory's abstract nature can sometimes lead to conclusions that are not easily testable with current technology. This clash between theoretical elegance and empirical evidence not only challenges the foundations of cosmological understanding, but also encourages ongoing dialogue and exploration within the scientific community. As our observational technologies advance, we may uncover new ways to test these intriguing ideas, further shaping our understanding of the universe. String theory posits that the fundamental building blocks of the universe are tiny vibrating strings rather than point-like particles. This idea leads to intriguing predictions about conditions that may have existed before the Big Bang, suggesting a pre-Big Bang phase featuring extra dimensions and unique energy states. But how could we find evidence to support these predictions? One of the key tenets of string theory is its ability to unify gravity with the other fundamental forces of nature. A compelling line of evidence would involve the detection of gravitational waves that correspond to the conditions of the early universe, potentially revealing echoes from a pre-Big Bang state. Scientists have been tirelessly exploring cosmic microwave background radiation, the afterglow of the Big Bang itself, for anomalies or patterns that might imply interactions with extra dimensions, as string theory suggests. Additionally, strings could produce unique particles, often referred to as superstrings, that might reveal themselves in high-energy phenomena. If particle accelerators like the Large Hadron Collider were to detect signatures of these elusive particles, it could bolster string theory's claims about a more complex, layered reality than currently understood. These discoveries would offer tangible proof that the universe may not be a singular event, but rather part of a more intricate, multidimensional tapestry. Furthermore, understanding anomalies in cosmic inflation could also provide vital clues. If models of inflation indicate a connection to string theory's higher dimensional framework, scientists could reverse engineer events that transpired before the Big Bang. Identifying such a link could transform our understanding of the universe's origins and lend credibility to string theory's expansive vision of reality. String theory stands at the intersection of two monumental pillars of modern physics, quantum mechanics and general relativity. At the heart of this theoretical framework is the idea that the fundamental building blocks of the universe are not tiny particles, but rather one-dimensional strings. These strings can vibrate at different frequencies, and their various modes of vibration correspond to different particles. This innovative perspective offers a potential reconciliation between the behaviors described by quantum mechanics and the geometric nature of spacetime outlined in general relativity. In a pre-Big Bang universe, the conditions are believed to be vastly different from those we experience today. Traditional theories predict singularities, points of infinite density, where the laws of physics break down. String theory, however, provides a smoother transition through these early moments. It suggests that the very fabric of spacetime could be shaped and influenced by these vibrating strings, allowing for a universe that is more interconnected and cohesive than previously thought. Before the Big Bang, the universe could have existed in a kind of stringy state where quantum fluctuations shaped the cosmic landscape. Furthermore, string theory incorporates additional dimensions beyond the familiar three. While our common experience tells us about 3 dimensions of space and 1 of time, string theory posits up to 9 spatial dimensions that are compacted and not directly observable. These extra dimensions play a crucial role in unifying the fundamental forces of nature, including gravity, electromagnetism, and the nuclear forces, bridging the gap between the quantum realm and the macroscopic world governed by general relativity. Ultimately, the beauty of string theory lies not just in its theoretical elegance, but also in its potential to describe a network of interactions that predates the classical understanding of time and space. Scientists are still exploring the implications of this theory, seeking both experimental evidence and insights that could illuminate the conditions leading to the Big Bang. As we continue to unravel the cosmos, string theory offers a captivating glimpse into the universe's intricate web, suggesting that the very essence of reality may be woven together in ways we are only beginning to understand. Black holes are among the most enigmatic objects in the universe, wielding incredible gravitational power that warps space and time. Their study offers profound insights into the nature of the cosmos. Some scientists propose that black holes might hold clues about conditions before the Big Bang, the event that marked the birth of our universe approximately 13.8 billion years ago. One fascinating theory suggests that black holes could be gateways to other universes or dimensions. According to this view, a black hole forms when a massive star collapses under its own gravity, creating a singularity, a point where density and gravitational forces become infinite. Some theorists speculate that these singularities could be connected to what came before our universe, potentially acting as conduits for matter and energy from previous cosmic epochs. Moreover, studying the radiation emitted by black holes known as Hawking radiation leads to intriguing implications about the information paradox and the nature of space-time itself. This concept challenges traditional views of how information is lost when objects fall into black holes. If it is possible for information to escape or be transformed, this could provide insights into the state of the universe before the Big Bang, suggesting a continuity or cyclical nature of cosmic evolution rather than a strict beginning with the Big Bang. While black holes themselves do not offer direct evidence of the universe's pre-Big Bang state, they underscore the limits of our understanding and ignite curiosity about the framework of existence. As researchers continue to explore the mystery surrounding these cosmic giants, they bolster the case for new theories that could potentially bridge the gap between current models of cosmology and the mysteries that lie beyond our observable universe. White holes, the theoretical opposites of black holes, present fascinating scenarios in our attempts to understand the origins of the universe. While black holes are known for their ability to pull everything inward, white holes would hypothetically expel matter, energy, and information. This unique property has led some scientists to speculate about their role in cosmic events, especially in relation to the birth of our universe. One intriguing scenario posits that white holes could be linked to the Big Bang. According to this idea, our universe may have emerged from a white hole that ejected energy and matter into a previously existing void. Such a process would offer a novel perspective on the question of what preceded the Big Bang. If white holes exist, they might provide a mechanism for the universe's birth, suggesting that they could spit out the very building blocks of galaxies, stars, and planets. Another possibility connects white holes to black holes through a theory known as wormholes. Some researchers speculate that a black hole could be connected to a white hole via a tunnel in space-time, known as a wormhole. In this model, matter that falls into a black hole might be ejected from a white hole in another location, or possibly even another universe. This interconnectedness could open up fascinating questions about the cyclic nature of the universe, where matter is continuously transformed and redistributed. While these concepts remain speculative and lack empirical evidence, they ignite our imagination about the cosmos. The nature of white holes challenges our understanding of physics and raises profound questions about the origins and fate of our universe. As scientists continue to explore these possibilities, they push the boundaries of cosmology, reminding us of the mysteries that still lie beyond our current comprehension. Black holes, those enigmatic regions of space where gravity is so intense that not even light can escape, have profound implications for our understanding of the universe. They challenge our traditional notions of space, time, and gravity. Recent research suggests that black holes could be more than just cosmic vacuum cleaners. They might also provide a glimpse into pre-Big Bang realities. This idea stems from the peculiarities of black hole singularities, the points at their centers where density becomes infinite. One intriguing theory is that black holes may serve as gateways or connections to other universes or dimensions. When matter collapses into a black hole, it raises questions about what happens within that singularity. If we consider what might emerge on the other side of a black hole, we could be looking at an entirely separate universe or a different state of reality altogether. This concept is not just science fiction. Some physicists propose that our own universe could have originated from the collapse of an earlier universe into a black hole, suggesting a cyclical model of cosmic rebirth. Equally thought-provoking is the idea that studying the quantum effects near black holes might reveal clues about conditions before the Big Bang. The merger of quantum mechanics and general relativity is a key challenge in modern physics. By examining the behavior of matter and energy under extreme gravitational forces, scientists hope to uncover insights about the very fabric of space-time and what might have existed before the universe as we know it took shape. Thus, Black holes are not mere cosmic oddities, but rather potentially vital components in unraveling the mysteries of the universe's origins. They encourage us to ponder profound questions about existence, the nature of reality, and the possibilities that lie beyond our observable universe. As we continue to delve into the intricate dance of gravity and spacetime, we edge closer to understanding how black holes could illuminate the hidden narratives of pre-Big Bang realities. The study of Hawking radiation offers intriguing insights into the fabric of our universe, particularly regarding the conditions that may have existed before the Big Bang. Proposed by the renowned physicist Stephen Hawking in 1974, this form of radiation emerges from black holes due to quantum effects near the event horizon. Essentially, it reveals that black holes can emit radiation and lose mass, eventually leading to their evaporation. This concept challenges long-held notions of black holes as entities that solely consume matter and energy, suggesting instead that they play an active role in cosmic processes. Understanding Hawking radiation goes beyond the fate of black holes. It also hints at the very nature of space and time. As we consider the state of the universe before the Big Bang, questions arise about what sort of matter and energy existed and how quantum mechanics might have influenced these primordial conditions. Hawking's theory bridges concepts of thermodynamics and quantum physics, suggesting a dynamic early universe, potentially rife with fluctuations that could have set the stage for the Big Bang itself. Moreover, Hawking radiation implicates a larger relationship between gravity and quantum mechanics, a relationship that we still strive to fully understand. The radiation suggests that the universe could possess properties of a quantum field, which might have existed in a chaotic state before the expansion of the cosmos. This era could have seen a mix of particles and antiparticles, dancing in a quantum ballet that would eventually give rise to the universe as we know it. In pondering the implications of Hawking radiation for pre-Big Bang conditions, we are invited to consider a universe full of potential. It emphasizes the crux of cosmological exploration, that even our deepest questions about time and existence may hinge on the delicate interplay of quantum-style phenomena unfolding at the very genesis of the cosmos. Through this lens, the enigma of the Big Bang transforms into a fascinating journey, inviting us to delve deeper into the mysteries that shaped our universe. Cyclic universe models present a fascinating alternative to the traditional understanding of the cosmos, which typically begins with a singular event known as the Big Bang. In these models, the universe does not have a static beginning. Instead, it undergoes an eternal series of expansions and contractions. This suggests that our current universe is just one phase in an infinite cycle of creation and destruction. The core idea behind these models is that the universe expands and eventually reaches a maximum size, after which it recollapses in a process called the Big Crunch. Following this contraction, conditions could become ripe for another Big Bang, leading to a fresh expansion phase. This cyclical process implies that each cycle could potentially erase the blow-up of the previous universe while setting the stage for a new one. Essentially, what occurs in the cosmos is not just a linear story, but a repeating drama of birth and rebirth. Moreover, cyclic models challenge the notion of a singular beginning, proposing that prior states of the universe might have existed long before our current one began. Some theories suggest that at the end of one cycle, if the universe collapses into a dense state, quantum mechanics might allow for a bounce instead of a singularity, paving the way for another Big Bang. The universe, in this scenario, maintains coherence over infinite cycles, with the potential for nuanced changes in physical laws or cosmic conditions that could affect each new expansion. In this light, cyclic universe models invite us to rethink our understanding of time, space, and the very fabric of reality itself. They weave together the gravitational dance of cosmic entities and the mysterious forces at play in the universe, challenging our perceptions and reminding us that the cosmos may be far more intricate and cyclical than a singular linear inception. These models not only captivate our imagination, but also prompt deeper inquiries into the nature of existence itself. Cyclic models present a compelling alternative to traditional Big Bang theories when it comes to explaining the universe's origins. The Big Bang theory proposes that the universe began from an extremely hot and dense singularity approximately 13.8 billion years ago. expanding rapidly and evolving into the cosmos we observe today. This theory suggests a linear progression of time and a single, unique origin point that has led to the current state of the universe. In contrast, cyclic models assert that the universe undergoes endless cycles of expansion and contraction. According to these theories, the universe expands from a singularity, just like in the Big Bang model, but rather than leading to a singular final state, it eventually reaches a peak and then contracts back to a dense state. After this contraction, the universe is thought to undergo another big bounce, starting the expansion cycle anew. This concept suggests an eternal series of births and deaths for the universe, allowing for a recurrent cosmic rhythm rather than a single beginning. One of the fascinating implications of cyclic models is how they address some of the unanswered questions and anomalies of the standard Big Bang theory, such as the uniformity of the cosmic background radiation. In a cyclic universe, the process of repeated expansion and contraction may help smooth out irregularities over countless cycles, potentially explaining the observed uniformity without relying solely on inflation theory. Cyclic models also raise profound philosophical questions about the nature of time, existence, and the ultimate fate of the universe. Instead of a beginning and an end, this perspective allows for a timelessness where the universe is in a constant state of regeneration. As we continue to explore these theoretical frameworks, the quest to understand the universe and our place within it evolves, revealing deeper insights into the cosmos and the laws that govern its existence. The concept of a cyclical universe suggests that the cosmos undergoes endless cycles of expansion and contraction. To support this fascinating theory, several pieces of evidence come into play, providing a broader context for our current understanding of the universe. One notable line of evidence lies in the study of cosmic microwave background radiation, or CMB. This faint afterglow of the Big Bang holds clues to the universe's early conditions. Some researchers suggest that irregularities in the CMB might hint at cycles of expansion, indicating patterns that could represent the remnants of previous universes. The uniformity and slight fluctuations observed in this radiation support models that envision the universe not as a one-time event, but part of an eternal sequence. Another intriguing aspect is the notion that certain physical laws, such as gravity and thermodynamics, might function differently under extreme conditions. Theoretical physicists postulate that as the universe contracts in a cyclical model, processes could lead to a rebirth akin to a cosmic reset. This might sidestep the singularities and paradoxes typically associated with the original Big Bang. Lastly, observations of supernovae and the rate of cosmic expansion further contribute to this narrative. As we delve deeper into space, the evidence of dark energy's role becomes apparent, propelling galaxies apart at a faster pace. Some theoretical frameworks suggest that dark energy might fluctuate across cycles, explaining both the current acceleration and the eventual deceleration towards another collapse. This interplay of accelerated expansion and gravitational pull paints a compelling picture of a universe that continually remakes itself, dancing between creation and destruction. The concept of a universe that undergoes multiple cycles of creation and destruction, often referred to as the cyclical universe theory, captivates the imagination of scientists and thinkers alike. This idea suggests that the universe can expand, contract, and then explode into a new cycle, continuously reshaping itself. To evaluate the plausibility of this model, scientists rely on both observational evidence and theoretical frameworks drawn from physics and cosmology. One of the key pieces of evidence lies in the study of cosmic microwave background radiation, the remnant heat from the Big Bang. This radiation provides a snapshot of the early universe and has been meticulously mapped. Scientists explore whether different phases of the universe's existence are discernible in this background radiation, looking for patterns that might indicate a past contraction or a previous universe. The dust and structures observed in the current cosmos also lend insight into its history and possible future cycles. In addition to observational data, theoretical physics plays a critical role. Theories such as quantum gravity and string theory introduce complex ideas about spacetime and how it might behave in extreme conditions. Some physicists propose models that incorporate a bounce, where a contracting universe reaches a point and then expands again, challenging traditional notions of a singular beginning. These theories are rich with implications, including the potential for infinite cycles, each leading to fresh iterations of cosmic phenomena. Ultimately, the evaluation of a cyclical universe hinges on the interplay between observation and theory. While current data seems to support a single expansion from an initial singularity, the evidence is not definitive. As technology advances and our understanding deepens, scientists continue to explore these fascinating possibilities, keeping the conversation alive about the nature and origins of our universe. The cosmological constant is a significant component in the field of cosmology, particularly when discussing the evolution of the universe and its earliest moments. This constant, often represented by a symbol, essentially acts as a measure of the energy density of empty space or vacuum. Its presence suggests a repulsive force that influences the universe's expansion rate. Because of this, it becomes a key player in theories about the universe's history, including considerations of the pre-Big Bang scenario. In many models of cosmology, the universe is thought to have begun with the Big Bang, a singular moment of rapid expansion from a hot, dense state. However, some theories propose that there may have been a phase before this event. The cosmological constant implies that the cosmos could have experienced a slow, accelerated expansion phase prior to the Big Bang, creating what is referred to as a pre-Big Bang era. This phase could have allowed for the smoothing out of irregularities in the universe, setting the stage for the highly homogeneous and isotropic universe we observe today. Intriguingly, the cosmological constant challenges our understanding of gravitational interactions and the foundational forces in the universe. The energy associated with the constant has been linked to the mysterious force of dark energy, thought to make up about 70% of the universe's total energy content. In this way, examining the cosmological constant not only sheds light on what came before the Big Bang, but also informs our understanding of the universe's current accelerated expansion. By delving into the implications of the cosmological constant, scientists are piecing together a more comprehensive picture of the universe's timeline. This exploration continues to push the boundaries of our knowledge, raising critical questions about the nature of space, time, and the very fabric of reality itself, all starting from that enigmatic moment before the Big Bang. The cosmological constant is a term that emerges from Einstein's equations of general relativity. It represents the energy density of empty space, or what we often refer to as dark energy. This concept holds significant implications for our understanding of the universe's evolution, especially when we consider the moments leading up to what we know as the Big Bang. If we look back in time, the cosmological constant suggests that the universe was not simply static or stable. Instead, it implies that there may have been an inherent energy driving the universe's expansion, even before the Big Bang itself. This idea hints at a dynamic, ever-changing environment where the fabric of space and time could have been shaped by forces that we are only beginning to understand. Moreover, the presence of a cosmological constant could help explain the accelerated expansion of the universe we observe today. As the universe expands, the gravitational pull of matter decreases, while dark energy, represented by the cosmological constant, remains constant. This balance may have influenced the universe's fate long before galaxies formed and stars ignited. As researchers delve deeper into cosmic history, they explore whether the cosmological constant could illuminate pathways to understanding the pre-Big Bang universe. It invites questions about whether our universe emerged from a previous state, or if it even shares a connection with other universes. Each new discovery adds layers to our understanding of the cosmos and challenges our perceptions of time, existence, and the very nature of reality itself. The cosmological constant is a fundamental concept in modern cosmology, originally introduced by Albert Einstein as a term in his equations of general relativity. This constant is tied closely to what we now call dark energy, a mysterious force that is driving the accelerated expansion of the universe. The cosmological constant can be understood as a type of energy density that fills space uniformly, exerting a repulsive gravitational effect. In the context of dark energy theories, the cosmological constant is often considered the leading candidate for explaining the observed acceleration of cosmic expansion. Observations of distant supernovae and the cosmic microwave background radiation reveal that our universe is not just expanding, but is doing so at an increasing rate. This unexpected behavior prompted scientists to consider the presence of dark energy, and the cosmological constant offers a simple, elegant explanation for this phenomenon. However, while using the cosmological constant provides a clear match to observable data, it raises profound questions about the nature of space and energy. The value of the cosmological constant predicted by quantum field theory vastly exceeds what we observe, creating a significant discrepancy known as the fine-tuning problem. This challenge has led to various speculative theories, suggesting alternative mechanisms for dark energy, such as dynamic forms of energy or modifications to existing gravity theories. These speculative theories, including ideas like quintessence or phantom energy, attempt to navigate the complexities of the cosmological constant. They present their own challenges for understanding the true nature of dark energy and its role in the fate of the universe. Ultimately, the cosmological constant remains a pivotal aspect of our quest to unravel the mysteries of dark energy, serving as a window into the fundamental workings of the cosmos. The quest to understand the conditions that preceded the Big Bang presents a significant challenge in cosmology, mainly due to the limitations of observational evidence. One of the primary hurdles is that the Big Bang represents the beginning of our universe's spacetime. This means any events or conditions leading up to this moment are steeped in uncertainty and are inherently difficult, if not impossible, to observe directly. The very fabric of spacetime itself was vastly different, if it existed at all, undermining our ability to gather concrete data from that era. Most cosmological theories propose that before the Big Bang, our universe was compressed into a point of infinite density known as a singularity. In this state, the laws of physics as we understand them break down, leaving us without a reliable framework to describe or predict the state of the universe prior to the Big Bang. Without a robust physical model, researchers struggle to generate testable predictions about pre-Big Bang conditions, which further complicates the pursuit of supporting observational evidence. Adding to these challenges, the cosmic microwave background radiation is one of the oldest observable signals, dating back to about 380,000 years after the Big Bang. It serves as a relic of the hot, dense state of the universe during its early moments, but does not provide insights into what occurred before this specific epoch. As theorists explore concepts like cosmic inflation or cyclic models, these models often present scenarios that can seem plausible, yet lack definitive proof, making it hard to establish a consensus within the scientific community. Finally, scientific exploration requires not only creativity, but also technological advancement. Instruments capable of probing such deep timeframes are still in their infancy. As we develop more sophisticated observational techniques, we may inch closer to understanding pre-Big Bang scenarios. Until then, scientists must blend theoretical physics with cautionary empiricism, striving to bridge the divide between the known universe and the enigmatic unknown that potentially existed prior to our universe's explosive birth. Advancements in technology and methods are increasingly transforming our understanding of the universe's origin, unlocking secrets that have long eluded scientists. High-powered telescopes, for instance, are at the forefront of these breakthroughs. With the ability to capture light from the farthest reaches of space, these instruments allow us to peer deeper into the cosmos than ever before. This view into the past helps us study the formation of galaxies and the early stages of the universe, offering clues about how everything began. Moreover, developments in computer simulations are playing a crucial role. These intricate models replicate the conditions of the early universe, allowing scientists to test hypotheses about cosmic evolution. By analyzing the interactions of fundamental forces and particles, researchers can explore scenarios that may have occurred shortly after the Big Bang. This approach enables a deeper understanding of phenomena like cosmic inflation, an explosive expansion that may have shaped the early universe. In addition to telescopic and computational advancements, new methods in particle physics are shedding light on the origins of the cosmos. Particle accelerators, like the Large Hadron Collider, allow scientists to recreate the high-energy conditions present just after the Big Bang. By studying the particles that emerge from these collisions, researchers can confirm theories related to the universe's formation, including insights into dark matter and energy, which remain some of the biggest mysteries of modern cosmology. Finally, Innovative technologies such as gravitational wave detectors have opened a new window into the universe. Gravitational waves carry information about cosmic events, such as the merging of black holes and neutron stars. By detecting these ripples in spacetime, scientists gain access to a wealth of data that enhances our comprehension of the universe's evolution. As these technologies continue to advance, our grasp on the origins of the universe will only deepen, revealing the profound complexities of our cosmic story. Scientists are eagerly anticipating several specific observations that could provide crucial insights into pre-Big Bang theories. One of the most compelling areas of interest lies in the cosmic microwave background radiation, a remnant from the early universe. Researchers aim to examine this radiation in greater detail, particularly looking for tiny fluctuations or anomalies that could hint at events before the universe reached its current state. These subtle variations might carry imprints of processes associated with cosmic inflation or other pre-Big Bang phenomena. Another area of focus involves the gravitational waves that may have been generated during the earliest moments of the universe. The detection of gravitational waves from events that occurred during or just after the Big Bang would serve as a powerful tool for testing various theories about what occurred before the creation of space and time as we understand it. Scientists are exploring advanced observatories, such as the Laser Interferometer Gravitational Wave Observatory, to pick up these elusive signals and decode the history hidden within them. Additionally, researchers are keen on understanding the distribution and behavior of dark matter and dark energy, which together dominate the universe's mass-energy content. Observations from upcoming large-scale surveys, like the Vera C. Rubin Observatory, will yield vast amounts of data on distant galaxies and their clustering patterns. Such findings can provide indirect clues about the pre-Big Bang conditions by helping scientists understand how structures formed and evolved in the universe. Lastly, advancements in particle physics, particularly through experiments at large particle colliders, may offer insights into energy scales and conditions that could have existed before the Big Bang. The search for new particles or interactions, especially those predicted by theories like string theory or loop quantum gravity, could extend our understanding beyond the traditional Big Bang narrative, ultimately revealing a more nuanced history of the cosmos. As these observations unfold, they promise to illuminate the mysteries of our universe, inviting us to explore the very fabric of reality itself. Current space missions play a pivotal role in enriching our understanding of the early universe, offering insights into its formation and evolution through innovative technologies and advanced instrumentation. Observations conducted from beyond Earth's atmosphere allow astronomers to study cosmic phenomena without the interference of the atmosphere, revealing details about ancient stars, galaxies, and the conditions that existed just moments after the Big Bang. For instance, the James Webb Space Telescope, launched recently, is enhancing our capabilities to observe distant galaxies that formed billions of years ago. Its powerful infrared sensors are able to detect light from these early galaxies, which has traveled through space for eons, providing clues about their composition and structure. By analyzing this ancient light, scientists can piece together a timeline of how galaxies evolved and began to cluster together, which is essential for understanding the universe's expansion. In addition to telescopes like Webb, missions like the European Space Agency's Planck satellite have offered profound insights into the cosmic microwave background radiation. This radiation is a remnant of the early universe, a faint glow left over from the Big Bang. By studying this radiation, scientists can glean critical information about the universe's age, its rate of expansion, and even the fundamental forces that triggered its rapid growth in the first few moments of existence. Moreover, ongoing missions studying extreme environments, such as those found at the edges of black holes or in the aftermath of supernova explosions, help unravel the complex interactions of matter and energy. Each mission adds a piece to the puzzle, illuminating the mysterious processes that shaped the cosmos. As technology advances and our observational capabilities grow, the mysteries of the early universe continue to unfold, inviting us to ponder our place in a vast and ever-evolving cosmos. The second law of thermodynamics is a fundamental principle of physics that states that in a closed system, the total entropy or disorder tends to increase over time. This concept is fascinating when we shift our focus to the origins of the universe, particularly the period before the Big Bang. While our understanding of the universe starts with this monumental event, many theories have emerged to ponder what, if anything, existed beforehand. In a universe governed by the second law, we see that it tends to evolve toward a state of maximum entropy. This raises intriguing questions about a pre-Big Bang state. If the universe was once in a highly ordered state, what could have caused it to transition into the disorder we observe today? Theories about this initial condition vary widely, some suggesting a singular, dense point, while others propose a far more complex scenario, potentially involving different dimensions or a multiverse, a sea of universes each with their own laws of physics. One prominent theory is the cyclic model, which posits that the universe undergoes an endless series of expansions and contractions. According to this view, the current state of the universe is not an absolute beginning, but rather a result of a previous contraction phase followed by a Big Bang. This creates an elegant loop where entropy and order interact in fascinating ways, suggesting that the universe may have rhythms beyond our current comprehension. As we continue to explore the cosmos and unravel its secrets, the second law of thermodynamics serves as a crucial backdrop. It compels us to ask deeper questions about the nature of existence itself. What came before the Big Bang may remain shrouded in mystery, but the pursuit of understanding this enigma pushes the boundaries of science and fuels our collective curiosity about the universe we inhabit. The concept of entropy plays a crucial role in our understanding of the universe, especially in discussions about the pre-Big Bang era. Entropy is often described as a measure of disorder or randomness within a system. In the context of the universe, it's a way to gauge the amount of energy that is unavailable to do work, affecting everything from the fusion reactions in stars to the fate of cosmic structures. Before the Big Bang, the universe is thought to have been in a state of extremely low entropy, meaning it was highly ordered and uniform. This seemingly bizarre notion challenges our intuitive understanding, because we typically associate disorder with chaotic beginnings. As the universe expanded and cooled after the Big Bang, entropy began to increase. This increase reflects the transition from a highly ordered state to one of immense complexity, where galaxies, stars, and planets formed over billions of years. The idea of a low entropy condition existing before the Big Bang also raises fascinating questions. It suggests that the universe might have started from a singularity, a point of infinite density and temperature. When coupled with theories of quantum physics, this presents intriguing possibilities about what could have preceded the Big Bang and whether the universe experienced a different phase or existence before our current timeline. Understanding entropy not only helps frame our discussions about the origins of the universe, but it also touches upon fundamental theories of cosmology and thermodynamics. The interplay of increasing entropy as the universe evolves continues to inspire scientists exploring the ultimate fate of the universe, making entropy a pivotal concept in grasping the cosmos's mysterious history from its inception to its infinitely intriguing future. To understand the early universe, we must delve into the concept of entropy. Entropy, in simple terms, measures the amount of disorder within a system. When we consider the conditions just moments after the Big Bang, the universe exhibited an astonishingly low level of entropy. This puzzling characteristic raises questions about how such a simple, uniform state could evolve into the highly complex cosmos we observe today. Scientists explore a range of theories to address this enigmatic low entropy state. One prominent explanation involves the notion of cosmic inflation. Shortly after the universe began expanding, a period of rapid growth expelled any irregularities and resulted in a remarkably homogeneous and isotropic cosmos. As this inflationary phase unfolded, the universe transitioned from a low entropy state, smoothing out any fluctuations, which set the stage for the later formation of stars, galaxies, and all the structures we see today. Another intriguing theory centers on the concept of gravitational entropy. Unlike ordinary matter, which tends to create disorder as it cools, gravity encourages a different kind of order. Dense regions collapse and clump together to form galaxies and galaxy clusters, effectively increasing the overall entropy of the universe over time. This dynamic may suggest that although the early universe was low in entropy, it contained the potential for tremendous disorder as matter condensed under gravitational forces. In addition to these ideas, some scientists propose that the early universe may have had unique characteristics that we do not fully understand yet. Quantum theories and concepts like string theory leave room for even more complexity within the initial conditions of the cosmos. Thus, ongoing research into these theories not only sheds light on the universe's inception, but also continues to inspire awe about the intricacies of cosmic evolution and the fundamental nature of reality. The cosmic microwave background radiation, or CMB, is often regarded as the afterglow of the Big Bang itself. This faint radiation fills the universe and provides a snapshot of its infancy, just about 388,000 years after the monumental event. Essentially, it gives us a glimpse into the state of the universe when it transitioned from an opaque plasma to a transparent expanse, allowing light to travel freely. This transition marked a significant moment in cosmic history, as it allowed us to observe the universe as it began to cool down and evolve. While the CMB is a powerful tool for examining the early universe, it also raises fascinating questions about conditions that preceded the Big Bang. One of the most intriguing ideas posited by scientists is that the universe may have undergone a period of inflation, a brief but rapid expansion. This theory not only accounts for the uniformity of the CMB, but also explains the tiny fluctuations captured in its temperature. These fluctuations are thought to relate to the seeds of all future cosmic structures, leading to the galaxies and clusters we observe today. Further analysis of the CMB provides insights into the fundamental nature of the universe, including its composition. By studying the CMB's anisotropies, or slight temperature differences, researchers have inferred the relative amounts of ordinary matter, dark matter, and dark energy in the cosmos. This understanding is vital for constructing models of the universe's evolution, yet it also hints at phenomena lying beyond our current understanding, underlying the possibility that pre-Big Bang conditions could be influenced by forces or dimensions we have yet to discover. As we continue to refine our models and gather more precise data from observatories and satellites dedicated to studying the CMB, we inch closer to answering the profound questions of our origins. Each piece of evidence helps to build a clearer picture of not only what followed after the Big Bang, but also what might have existed before it. While we may not yet have definitive answers, the CMB continues to serve as a crucial tool in our quest to understand the enigmatic beginnings of our universe. The cosmic microwave background radiation, or CMB, serves as a faint afterglow of the Big Bang, filling the universe with a steady light. It acts as a snapshot from about 380,000 years post-Big Bang, when the universe cooled enough for atoms to form. This radiation is not uniform. It features minute variations or anomalies. These peculiarities can reveal significant insights about the early universe and challenge or support various pre-Big Bang theories. One of the most intriguing aspects of these anomalies is how they inform our understanding of conditions before the Big Bang. Some pre-Big Bang hypotheses suggest scenarios like a cyclic universe, where the cosmos undergoes endless cycles of expansion and contraction. Certain anomalies in the CMB, particularly those resulting from gravitational waves from the inflationary phase, bolster the case for such models. They indicate that fluctuations in density occurred even before the Big Bang, providing evidence of reality beyond our current temporal boundaries. Conversely, the anomalies can also generate skepticism towards some pre-Big Bang models, mostly those predicting a simple, smooth universe. The irregularities present in the CMB, sometimes more clumped in specific areas, hint at complex processes that possibly occurred before the emergence of our universe. This complexity often aligns more closely with an inflation theory rather than a static or simplistic pre-Big Bang condition. Ultimately, the cosmic microwave background acts as a crucial piece of the puzzle in modern cosmology. Its anomalies provide vital clues that both support and challenge existing theories about the universe's origins. As our observational techniques improve and as new data emerges, the insights gleaned from the CMB may continually reshape our understanding of not just how the cosmos began, but also what might have existed before its inception. The cosmic microwave background, often abbreviated as CMB, serves as a remnant glow from the early universe, a relic dating back to just a few 100,000 years after the Big Bang. Scientists have learned that this faint relic radiation is nearly uniform across the sky, providing a snapshot of the universe when it was a hot, dense soup of particles. The CMB reveals critical information about the conditions of the universe at that time, offering a window into its birth and infancy. Through detailed observations of the CMB, particularly its tiny temperature fluctuations, researchers have uncovered essential clues about the universe's composition. For instance, these fluctuations correspond to regions of differing density, which eventually led to the formation of galaxies and large-scale structures we see today. This data has helped scientists estimate the percentage of matter, and dark energy within the universe, painting a clearer picture of its overall makeup. Moreover, the CMB provides evidence supporting the inflationary model of the universe. Inflation theory suggests that there was an exponential expansion of space within the first moments of the universe. The patterns in the CMB align remarkably well with predictions from this theory, reinforcing our understanding of how the universe transitioned from a smooth infant state to the complex structure we observe now. Finally, studying the CMB allows scientists to delve into the fundamental questions surrounding the universe's fate. By analyzing its temperature and polarization, researchers can glean insights into cosmic expansion, leading to a better understanding of whether the universe will continue to expand indefinitely or eventually contract. Thus, the cosmic microwave background not only illuminates the early moments of the universe, but also connects to the larger narrative of cosmological evolution and destiny. Pre-Big Bang theories delve into the origins of our universe and challenge our current understanding of time, space, and reality itself. These theories often speculate about what happened before the Big Bang, suggesting scenarios like a cyclic universe or quantum fluctuations in a timeless state. Such ideas force scientists to rethink the limits of existing methodologies, urging a re-evaluation of how we frame questions about the cosmos. One significant implication involves the nature of evidence in cosmology. Traditionally, scientific inquiry has relied on observable data. However, since the pre-Big Bang realm lies beyond what we can measure, it pushes researchers to explore more abstract theories. This curiosity fosters innovation in scientific tools and models, engaging fields like quantum physics and general relativity in ways that could illuminate the very fabric of reality, even if direct observation remains elusive. Moreover, pre-Big Bang theories challenge the linear perspective of time and causality that governs much of modern science. If time itself began with the Big Bang, then our standard methods of experimentation and observation may become inadequate. Scientists might need to embrace a more philosophical approach, considering multiple dimensions of reality and adopting theoretical frameworks that open new avenues of inquiry without being strictly bound to empirical validation. Ultimately, the debate surrounding pre-Big Bang theories enriches scientific methodology by highlighting the need for interdisciplinary collaboration. By merging insights from cosmology, physics, and even philosophy, researchers can develop a more comprehensive understanding of the universe. This pursuit not only heightens our awareness of the complexities surrounding cosmic origins, but also sharpens our scientific vision, pushing the boundaries of what we consider possible. In the realm of scientific inquiry, assumptions serve as foundational pillars upon which theories are built and explored. When discussing constructs like a pre-Big Bang universe, these assumptions play a critical role in shaping our understanding of the cosmos and influencing the paths we take in theoretical exploration. Scientists begin with a set of established principles and notions about the universe, such as the laws of physics and the nature of time and space. These principles help frame the questions scientists ask and the interpretations they make about the universe's origins. One significant assumption is that the laws of physics, as we understand them today, apply uniformly across time and space. However, when we delve into concepts like what existed before the Big Bang, we encounter challenges. Many theories suggest that our current understanding of time and space may not hold in the same way before the Big Bang, because the Big Bang itself marks the beginning of time as we know it. This raises profound questions about causality and the nature of existence itself. Theories like the cyclic universe, the multiverse, or the idea of quantum fluctuations provide fascinating possibilities for a pre-Big Bang scenario. Each of these theories is rooted in particular assumptions about reality. For instance, the cyclic universe model assumes that the universe undergoes endless cycles of expansion and contraction, suggesting a timeless regime before each cycle. Meanwhile, the multiverse theory posits that our observed universe might be just one of many, each with its own unique properties. These differing assumptions lead to distinct interpretations and implications about our universe's origins. Ultimately, the exploration of a pre-Big Bang universe highlights the interplay between assumptions and scientific debate. Researchers constantly evaluate and re-evaluate these foundational beliefs as they gather new observational data and develop advanced technologies. This dynamic process of inquiry not only fuels our understanding of the universe's past, but also showcases the evolving nature of science itself, reminding us that our quest for knowledge is as boundless as the cosmos we seek to understand. The understanding of the cosmos before the Big Bang has long been a tantalizing mystery for scientists and cosmologists. Traditional scientific models, which primarily address the universe's evolution beginning from that monumental event, are now being reshaped by emerging theories that delve into what might have existed prior to that moment. As fresh data and insights from quantum physics, string theory, and cosmic inflation arise, models are evolving to incorporate these revolutionary ideas. One significant development is the consideration of various pre-Big Bang concepts, such as the cyclic universe. This theory posits that the universe undergoes endless cycles of expansion and contraction, suggesting that what we perceive as the Big Bang is merely the latest in a series of cosmic bounces. Scientific models are adapting to accommodate this idea, trying to reconcile the existing observations with the possibility of an eternally inflating universe. Another area of exploration involves quantum gravity and how it might explain conditions before the Big Bang. Theories such as loop quantum gravity suggest that time and space may have a different nature at these extreme scales. Researchers are now working on models that integrate quantum effects into the framework of cosmology, while also examining how these phenomena could influence the birth of the universe itself, challenging our classical perception of time. Adapting these models is no small feat. It requires a delicate balance of observed evidence, theoretical consistency, and mathematical rigor. As scientists gather more observational data from cosmic microwave background radiation or gravitational waves, they will continue to refine these models. This iterative process exemplifies the dynamic nature of science, where our understanding of the universe is continuously molded by new theories and discoveries. With every revelation, scientists come closer to piecing together the complex puzzle that predates the Big Bang, sparking wonder about what the cosmos may have looked like in those primordial days. The pre-Big Bang universe remains one of the most profound mysteries in modern cosmology, and disciplines like mathematics and computer science play a crucial role in unlocking its secrets. Mathematics serves as the language of the universe, providing the framework for formulating theories about its origins. For instance, equations derived from general relativity help scientists describe the curvature of spacetime and model conditions that could have existed before the Big Bang. Through mathematical rigor, physicists can explore theoretical concepts such as singularities and quantum fluctuations, which are essential in understanding the state of the universe during its infancy. Computer science complements these mathematical frameworks by enabling complex simulations and data analysis. With the help of advanced algorithms and computational power, researchers can create models to simulate different scenarios that might have occurred before the universe as we know it began. These simulations allow scientists to visualize and manage vast amounts of data, testing hypotheses about early universe conditions. By processing languages that encode physical theories, computers help solve equations that are otherwise intractable for human minds alone. In the realm of theoretical physics, string theory and loop quantum gravity are two examples where computer science and mathematics intersect. String theory proposes that the fundamental building blocks of the universe are not point-like particles, but rather one-dimensional strings. This theory requires sophisticated mathematical tools and computational methods to explore its implications, particularly in contexts where traditional physics struggles. Loop quantum gravity, on the other hand, seeks to reconcile quantum mechanics with gravity and involves complex calculations that are often addressed using computer simulations. Ultimately, the collaboration between these disciplines not only enhances our understanding of the possibilities of a pre-Big Bang universe, but it also challenges our perceptions of reality. As scientists continue to investigate the origins of the cosmos, the integration of mathematics and computer science will remain pivotal, pushing the boundaries of theoretical knowledge and unlocking new dimensions of inquiry into the very fabric of existence itself. The quest to understand pre-Big Bang theories is a complex journey that requires the combined expertise of various scientific disciplines. Interdisciplinary collaborations bring together physicists, cosmologists, mathematicians, and philosophers, all contributing unique perspectives and skills. This synergy is crucial, as the phenomena surrounding the beginnings of our universe challenge contemporary understanding, requiring innovative approaches that single fields might not achieve alone. For instance, physicists create the theoretical frameworks that guide our understanding of the universe's early moments, including concepts like quantum gravity and string theory. Meanwhile, mathematicians develop complex models that can either support or challenge these theories, providing a rigorous foundation upon which to build further inquiries. Philosophers, on the other hand, explore the implications of these theories, pushing the boundaries of what we consider possible and stimulating discussions around the nature of existence and the cosmos. Moreover, interdisciplinary teams often engage in experimental design, where different expertise converges to devise tests for these theoretical frameworks. Astronomers, utilizing powerful telescopes and advanced detection methods, gather observational data that can validate or refute pre-Big Bang models. This collaboration helps ensure that the created tests are both scientifically robust and practically feasible, enhancing the credibility of the findings. Ultimately, the role of interdisciplinary collaborations in developing tests for pre-Big Bang theories cannot be overstated. By blending various scientific insights and methodologies, researchers can tackle the profound questions about the universe's origins with greater creativity and rigor. As our understanding progresses, these cooperative efforts will likely illuminate even more about the mysteries that lie hidden behind the cosmic curtain of time and space. The study of cosmic beginnings is a complex and multifaceted endeavor that benefits significantly from the collaboration of researchers across various scientific disciplines. Physicists, astronomers, chemists, geologists, and even biologists all play vital roles in piecing together the history of the universe from its inception to the present day. Each discipline brings its unique perspective, tools, and methodologies to form a comprehensive understanding of cosmological phenomena. Physicists often lead the charge in exploring fundamental concepts such as the nature of dark matter and dark energy, which together make up a significant portion of the universe. They use theoretical models and powerful particle accelerators to experiment with conditions similar to those just after the Big Bang. Meanwhile, astronomers complement this work by collecting light from distant galaxies, examining the cosmic microwave background radiation, and studying supernovae, all of which provide essential clues about the universe's expansion and age. Their observations help validate or challenge theoretical predictions laid out by physicists. Chemists contribute to this multidisciplinary approach by studying the elemental composition of celestial bodies and the chemical processes occurring in stars and nebulae. This information is crucial for understanding how the first elements were created and how they have evolved through processes like star formation and supernova events. Geologists also add depth to the conversation by examining planetary bodies within our solar system, gaining insights into the geological history that informs us about the conditions that might have led to life on Earth. By sharing data, techniques, and findings, researchers from these various fields create a richer, more nuanced picture of cosmic beginnings. Conferences and collaborative studies allow for dialogue and cross-pollination of ideas, leading to innovative theories. This integration of knowledge not only deepens our understanding of the universe's origins, but also sparks new questions, inviting even more inquiry into the unknown aspects of our cosmos. In this way, the collective effort of diverse scientific disciplines fuels a continuous cycle of discovery in the ever-evolving narrative of the universe. Recent astronomical discoveries have vastly expanded our understanding of the cosmos and sparked intriguing discussions about conditions preceding the Big Bang. A particularly significant revelation comes from studies of cosmic microwave background radiation, remnants from the early universe. These observations provide valuable insights into the universe's evolution and suggest possibility scenarios that challenge our traditional perceptions of cosmic origins. Another fascinating aspect lies in the detection of gravitational waves. Since their first observation in 2015, these ripples in spacetime have revealed uncharted territories of physics. Some researchers have even proposed that certain gravitational wave signatures could point to prior events occurring before the Big Bang, leading to theories of a cyclical universe or earlier cosmic collapses. This notion posits that the universe may have undergone endless expansion and contraction phases, creating a rhythm of cosmic rebirth. Moreover, advancements in telescope technology, particularly the James Webb Space Telescope, have allowed astronomers to peer deeper into the universe than ever before. With this unprecedented view, scientists are uncovering galaxies formed only a few 100 million years after the Big Bang. These discoveries raise questions about the nature of matter and energy, suggesting that the universe could be more complex than a simple origin point marked by the Big Bang alone. Lastly, we must consider the implications of dark matter and dark energy. These components dominate the cosmos but remain largely elusive. Their behavior and interaction may hold the key to understanding not only our universe's structure, but what might have existed before it came into being. Each discovery presents more pieces in the grand cosmic puzzle, inviting us to contemplate what lies beyond our current comprehension of the universe's beginnings. Recent discoveries in the cosmos often act as a catalyst, reshaping or reinforcing our existing theoretical models of the universe. For example, the detection of gravitational waves opened a new window into understanding black holes and neutron stars, affirming aspects of Einstein's theory of general relativity while also challenging certain classical notions of these phenomena. Each detection not only confirms long-held beliefs, but also adds layers of complexity to our understanding of the very fabric of spacetime. In addition, the discovery of exoplanets, especially those in the habitable zones of their stars, has profound implications for the search for life beyond Earth. These findings support and expand the theories of planetary formation and evolution. Scientists have had to refine their models of how planets form and develop under varied conditions, leading to more sophisticated predictions about where life might exist in the universe. This dynamic interplay between discovery and theory reveals the ever-evolving nature of scientific understanding. Moreover, the application of advanced technologies, such as deep space telescopes, has expanded our horizon, enabling us to observe cosmic phenomena that were previously undetectable. The images and data collected help reinforce the Big Bang theory, providing concrete evidence of cosmic microwave background radiation and distant galaxies formation. As a result, scientists are not only confirming pre-existing models, but also expanding them to incorporate new types of astronomical observations. Finally, these interactions between discoveries and theoretical models highlight the scientific process itself, which thrives on revision and rebirth. As new data emerges, models are adjusted, revealing the flexibility and complexity of scientific theories. This ongoing refinement ensures that our grasp of the universe remains not just accurate, but also profoundly insightful, continuously driving humanity's quest for knowledge about the cosmos. The story of universal origins is a constantly evolving narrative, shaped by new discoveries and advancements in science. Each new finding, whether it be related to cosmic microwave background radiation, the formation of galaxies, or the behavior of dark energy, adds depth to our understanding of how the universe began and evolved. Scientists meticulously analyze these findings and place them within a broader framework, seeking connections that link seemingly disparate pieces of information. 11 billion years ago, the universe emerged from a singularity during an event known as the Big Bang. Since then, a rich tapestry of ingredients, such as stellar explosions and black holes, have played pivotal roles in shaping what we see today. When new data arrives from telescopes or satellite missions, researchers integrate this information by correlating it with existing theories. For example, findings from the Hubble Space Telescope or the Planck satellite can either reinforce current models or challenge scientists to rethink established views. Researchers regularly convene in collaborative settings to discuss these developments. Workshops and conferences serve as platforms for scientists to share their insights and research. It is in these discussions that new findings are debated, tested, and refined. When significant evidence arises, it can prompt a re-evaluation of certain aspects of the cosmic narrative, pushing the boundaries of our understanding and sometimes leading to breakthrough theories. Publications in scientific journals also play a crucial role in disseminating new knowledge. By documenting findings and methodologies, scientists ensure their work can be peer-reviewed and integrated into the wider scientific discourse. As new layers of understanding emerge, the narrative of universal origins grows ever richer, resembling an intricate puzzle where each new piece enhances the overall picture of our cosmos. This dynamic process invites all of us to marvel at the vast and uncharted territories of the universe. Symmetry plays a critical role in our understanding of the universe, particularly when we delve into theories about the era preceding the Big Bang. In physics, symmetry often implies that certain properties remain invariant even when changes occur. For instance, if you were to rotate a sphere, its appearance remains unchanged. In the realm of cosmology, this principle helps physicists formulate theories about the fundamental nature of reality. Before the Big Bang, theoretical physics proposes that the universe might have been governed by different laws, potentially possessing symmetrical characteristics. This symmetrically balanced state could suggest a universe where forces, matter, and energy existed in harmony. In such scenarios, symmetry aligns seamlessly with concepts like inflation, where the rapid expansion of space might be attributed to a balanced energy field. The uniformity in cosmic microwave background radiation offers a glimpse into how this symmetry might have influenced the homogeneous nature of the early universe. Conversely, the absence of symmetry introduces a rich tapestry of possibilities. If the pre-Big Bang universe lacked symmetry, it could lead to diverse interactions and variations in matter and energy distributions. This breaking of symmetry might result in the chaotic conditions that eventually gave rise to the complexities we observe today. Understanding how these symmetry breakings occurred is essential, as it could illuminate why, after the Big Bang, the universe evolved into a state that is far from uniform, with galaxies, stars, and planets. Ultimately, studying symmetry, or the lack thereof, in pre-Big Bang theories not only contributes to our grasp of cosmic inception, but also bridges the gap between our current understanding and the enigmatic origins of the universe. The interplay of symmetry and asymmetry in this context invites endless exploration into the fundamental forces that shape our reality. Symmetry plays a crucial role in our understanding of the universe, especially when we delve into its origins before the Big Bang. At its core, symmetry involves the idea that certain properties remain unchanged under specific transformations. Scientists harness these concepts to propose theories about the early state of the universe, where traditional physics begins to stretch its limits. One key aspect is the symmetry seen in fundamental forces. For example, during the first moments following the Big Bang, the universe is believed to have been in an extremely hot and dense state where gravity, electromagnetism, the strong force, and the weak force were unified. This symmetry means that the laws governing these forces were indistinguishable, suggesting a kind of cosmic equilibrium. If the universe began in this highly symmetric state, it could allow scientists to extrapolate back to understand how forces evolved as it expanded and cooled. Moreover, scientists also explore the concept of cosmic inflation, a rapid expansion that happened nearly instantly after the Big Bang. During this inflationary period, the universe began to smooth out, leading to a more homogeneous state that preserves symmetry. The fluctuations in this symmetry might have given rise to the clumpiness we observe in galaxies today. By analyzing the patterns of cosmic microwave background radiation, scientists can trace these remnants of symmetry breaking, giving clues about conditions near the inception of the cosmos. Ultimately, when scientists examine symmetry in relation to the universe before the Big Bang, they are not just investigating a moment in time, but a landscape of infinite possibilities. These insights shape our current theories about cosmology and help construct a coherent narrative about the universe's beginnings, despite the inherent mysteries that still lie beyond our reach. Through symmetry, we not only gain a window into the past, but also illuminate the fundamental principles that govern the universe. In the quest to understand the origins of the cosmos, researchers heavily rely on symmetry-based theories, which suggest that the universe operates under fundamental principles of symmetry. One of the most striking examples comes from particle physics, particularly the Standard Model of particle physics. Scientists examine how elementary particles behave and interact under different conditions. Specifically, they look for patterns that affirm the idea of symmetry, which helps to unify different forces in the universe. One crucial piece of evidence comes from the discovery of the Higgs boson in 2012 at the Large Hadron Collider. This particle is vital to the theory, as it supports the mechanism that gives mass to other fundamental particles. Researchers analyze the properties of the Higgs boson to see if they match predictions made by symmetry theories. By testing how this particle interacts with other particles and measuring its mass and decay channels, scientists gather critical data that confirm or challenge existing models. Cosmic microwave background radiation is another pivotal area of study. This faint glow permeating the universe is a remnant of the Big Bang, and it carries with it information about the early universe. Researchers explore the uniformity and slight fluctuations in this radiation to glean insights into the symmetry underlying cosmic structures. These patterns can indicate whether the expansion of the universe and the distribution of matter align with symmetry predictions, revealing the fundamental nature of cosmic origins. Finally, galaxies themselves serve as a cosmic laboratory. Astronomers observe their formation and distribution throughout the universe. If symmetry theories hold true, we would expect to see certain regularities in how galaxies cluster and evolve. By mapping these structures and studying their motion, researchers can validate or refine symmetry-based models, refining our understanding of both the large-scale architecture of the universe and the underlying physical laws that govern it. Each discovery brings us a step closer to unveiling the intricate tapestry of our cosmos. The pre-Big Bang universe is an intriguing concept that invites us to explore the possible conditions and structures of the cosmos before time and space as we know them began. At this moment in the universe's history, everything we understand about physics seems to hit a brick wall. This is where abstract mathematical constructs come into play, offering a framework to theorize about phenomena that are otherwise beyond our understanding. Mathematics has always been a vital tool in cosmology. It provides a language to articulate hypotheses, allowing scientists to model complex concepts. In the case of the pre-Big Bang era, certain mathematical frameworks like string theory or quantum gravity help define parameters that might govern the universe's initial conditions. These constructs can lead to scenarios where space and time behave differently than our current models suggest, presenting a potent playground for theoretical physicists. Through abstraction, mathematicians and physicists can propose ideas like the multiverse or the cyclical universe, paving the way for new interpretations of existence itself. Here, one can think of different geometric shapes or dimensional theories as potential descriptors of the universe's fabric before the Big Bang unfolded. Such models allow us to imagine what types of forces and particles could have influenced the cosmos at its inception, suggesting that our universe might just be one instance in a vast array of cosmic possibilities. Ultimately, while abstract mathematics cannot provide empirical evidence directly, it serves as a beacon illuminating potential paths of inquiry. This creative approach not only stretches our understanding of the universe, but also emphasizes the remarkable interplay between math and physical reality. Through this lens, we begin to appreciate the depth of the question, what came before it all? Even as we grapple with the unknown, mathematics compels us to dream and theorize in search of deeper truths about our origins. Abstract thinking is a fundamental component of the scientific process, particularly when it comes to exploring the origins of the universe. This type of thinking allows scientists and theorists to step beyond the tangible and the immediate, embracing concepts that are not directly observable. For instance, when considering the Big Bang theory, abstract thinking enables us to visualize conditions of the universe just after its beginning, a time when traditional sensory experience doesn't apply. Through abstraction, scientists formulate hypotheses and models that explain complex phenomena. These can range from the nature of dark matter to the behavior of quantum particles in extreme environments like black holes. Such abstract concepts may initially seem far removed from our everyday experiences, yet they are essential for developing frameworks that can predict the behavior of the universe. This mental flexibility opens up possibilities for new ideas and insights that linear thinking might miss. Moreover, abstract thinking is vital for connecting disparate pieces of information. By synthesizing knowledge from various fields such as physics, cosmology, and even philosophy, scientists can create a more holistic view of the cosmos. This interconnectedness leads to more robust hypotheses about universal origins and encourages collaboration across disciplines, enriching the pursuit of understanding. In the end, abstract thinking not only fuels curiosity and innovation, but also propels scientific inquiry. As we continue to ask profound questions about the universe and our place in it, this way of thinking is instrumental in shaping a deeper comprehension of the complexities of existence, driving us closer to uncovering the mysteries that surround our origins. Before we dive into speculative physics theories that explore possibilities before the Big Bang, let's first consider what we know. The Big Bang is widely recognized as the beginning of our universe, marked by an expansion from an incredibly hot and dense state. But what, if anything, existed prior to this monumental event? This remains one of the most tantalizing questions in cosmology. One perspective comes from the theory of cosmic inflation. This idea suggests that shortly after the Big Bang, the universe underwent an exponential expansion. Some scientists propose that this inflationary phase could be a continuation of an earlier cyclic universe. In this model, the universe experiences an endless series of expansions and contractions. Each cycle may have its own Big Bang, leading to a cosmos that is eternally reborn. This theory not only offers a scenario for a pre-Big Bang state, but also challenges our conventional understanding of time itself. Another intriguing avenue is the concept of a multiverse. Some speculative theories suggest that our universe is just one of countless others, bubbling up in a vast sea of universes, each with its own set of physical laws and constants. In this view, what came before our Big Bang might not fit within our standards of existence, as it may belong to a realm of other universes, some potentially preceding ours in a different form. The idea is as mind-boggling as it is liberating, hinting that our universe might be just one chapter in an infinite story. Lastly, there's the consideration of quantum mechanics and its implications. The famous physicist Stephen Hawking proposed that the universe has no boundary, and quantum fluctuations could imply a scenario in which time itself simply didn't exist as we understand it before the Big Bang. This line of thought challenges our fundamental perceptions of causality and time, piecing together the idea that the universe may have emerged from a quantum state that defies conventional logic. Speculative physics, in this sense, not only broadens our horizons in terms of understanding the origins of our universe, but it also invites us to rethink the very nature of existence itself. The quest to understand the conditions that existed before the Big Bang has fascinated cosmologists for decades. Among the most intriguing speculative theories is the idea of a multiverse. This theory posits that our universe is just one of many, each with its unique properties and laws of physics. Some proponents suggest that different universes could have emerged from a quantum fluctuation in a vast cosmic framework. The imagination of scientists is captured by the thought that the Big Bang might represent not a beginning, but rather a transition from one universe to another. Another compelling idea comes from the concept of cyclic universes. This theory suggests that the universe undergoes a continuous series of expansions and contractions, like a cosmic heartbeat. Each cycle begins with a Big Bang and ends with a big crunch, only to be followed by another expansion. This idea challenges the notion of a single beginning point in time, suggesting instead that infinity may be woven into the fabric of the cosmos. Cyclic models provide an exciting canvas for theorists who want to understand how the universe might regenerate itself through time. Then there's the proposal of a pre-Big Bang scenario rooted in string theory. According to this perspective, the fundamental elements of our universe are not particles but tiny, vibrating strings. In string cosmology, the pre-Big Bang universe could have been a different state of existence, characterized by higher dimensional spaces and differing physical laws. This pre-universe could have contained fluctuations that eventually led to the conditions we now identify with our universe's birth. Each of these ideas emphasizes a vision of the cosmos that extends beyond the conventional understanding of time, space, and existence. As theories evolve, they challenge our perspectives, inspiring even deeper inquiries into what might have preceded the magnificent unfolding of the universe as we know it. While concrete evidence for these speculative scenarios remains elusive, they reflect humankind's enduring desire to unravel the ultimate mysteries of the universe. Speculative theories in science often present fascinating ideas that challenge our understanding of the universe. However, one of the primary obstacles these theories face is the lack of empirical validation. Empirical validation relies on observation and experimentation to support a hypothesis. When a theory is too speculative, it may propose scenarios or entities that are difficult, if not impossible, to observe or measure with current technology. This makes it challenging to gather the necessary data to either support or refute these ideas. Another significant hurdle involves the criteria of falsifiability. For a theory to hold scientific weight, it needs to be testable. This means there should be a potential observation that could demonstrate it to be incorrect. Many speculative theories propose concepts that are so abstract or grand, such as alternate dimensions or exotic forms of matter, that they do not lend themselves to straightforward testing. As a result, they may linger in the realm of philosophical debate rather than empirical science. Moreover, speculative theories often compete with established scientific frameworks. When a new idea emerges, it may contradict existing theories that have a solid basis in empirical data. The scientific community tends to favor ideas that can be easily integrated into existing knowledge. A speculative theory that challenges established concepts without sufficient evidence can be met with skepticism. This can slow its acceptance, limiting opportunities for research and testing. Lastly, funding and resources pose another challenge for speculative research. Scientific projects often require significant financial investment, and funding bodies usually prioritize proposals with clear, achievable goals grounded in existing knowledge. Speculative ideas may not attract the necessary funding, restricting the ability of researchers to explore these intriguing concepts further. Thus, while the journey of scientific discovery is marked by innovative and daring ideas, speculative theories often find themselves navigating a complex landscape of validation, skepticism, and resource limitations. Cosmic strings and brains are fascinating concepts in theoretical physics, contributing significantly to our understanding of the universe's earliest moments. Cosmic strings are hypothetical, one-dimensional topological defects that could have formed during phase transitions in the early universe. These defects may have been created when the universe cooled after the Big Bang, similar to how cracks form in ice as it freezes. Their existence, though unconfirmed, would have profound implications for cosmology and the fabric of the cosmos. Brains, or membranes, are higher-dimensional objects in string theory, a leading candidate for a unified theory of all forces in the universe. In some models, our entire universe could be thought of as a three-dimensional brain floating within a higher-dimensional space. This framework allows for a unique perspective on cosmic events. For example, interactions between membrane-like structures could potentially explain the origin of the universe itself, hinting that our own Big Bang might have been the result of two brains colliding. The connection between both cosmic strings and brains and the pre-Big Bang universe lies in their ability to shape the early conditions of the cosmos. The strings could influence the distribution of matter and energy in the universe, leaving behind a characteristic signature in the cosmic microwave background, the afterglow of the Big Bang. Similarly, brains could interact in ways that result in inflationary scenarios, where the universe experienced a hyper-rapid expansion, stretching and smoothing out before settling into the relatively stable cosmos we see today. Ultimately, while these ideas are still highly theoretical and require further empirical evidence, they open an exciting window into the conditions that may have existed before the Big Bang. As researchers continue to explore these concepts, they offer tantalizing hints at the complex and dynamic processes that could have shaped the universe we inhabit, underscoring just how little we truly understand about the origins of everything. The idea of cosmic strings arises from theoretical physics, particularly in the context of the early universe. These hypothetical structures are one-dimensional defects that could have formed during phase transitions in the very early moments after the Big Bang. They are often linked to various models of cosmology that attempt to explain the origins and evolution of the universe before inflation. the rapid expansion that followed the Big Bang. To support the hypothesis involving cosmic strings, scientists look for specific signatures in the cosmic microwave background radiation, often referred to as the afterglow of the Big Bang. If cosmic strings existed, they would leave distinct patterns in this radiation, particularly in the form of gravitational waves. Such waves would create fluctuations, producing unique temperature variations in the cosmic microwave background that could be detected by sensitive instruments. Additionally, researchers are investigating the large-scale structure of the universe for signs of cosmic strings. Their presence could manifest as alignments or clusters of galaxies, shaped by the gravitational influence of these strings. By observing how galaxies are distributed and how they move, scientists can gather clues regarding the existence of these fascinating structures. While direct evidence remains elusive, theoretical models continue to evolve, and as observational technology advances, the potential to gather supporting data increases. The quest for understanding cosmic strings is a testament to humanity's desire to unravel the mysteries of the universe's earliest moments, offering a glimpse into a time shrouded in cosmic uncertainty. Brain cosmology introduces a fascinating perspective in the discussion of universal origins by positing that our universe is a three-dimensional surface, or brane, existing within a higher dimensional space. This idea stems from string theory, which suggests that the fundamental building blocks of nature are not point-like particles, but rather tiny, vibrating strings. In this framework, our observable universe is just a slice of a more complex multiverse, where additional dimensions beyond the familiar three of space and one of time exist. Integrating brain cosmology with other theories requires a nuanced approach, as it complements ideas like the Big Bang and inflationary models. For example, some brain cosmology models propose that the Big Bang occurred due to a collision between our brain and another brain in this higher dimensional space. This collision could create significant energy and matter, giving rise to the universe as we know it. Such interactions are thought to lead to the expansion of our universe, aligning with the observational evidence of its ongoing expansion. Moreover, brain cosmology resonates with quantum gravity theories. It offers potential resolutions to problems like singularities and the nature of black holes. Previous models faced challenges in reconciling the behavior of gravity at quantum scales, but the high-dimensional settings of brain theory allow for a more cohesive understanding of these phenomena. In this context, black holes may not be mere endpoints of collapsing matter, but rather essential elements of the brain structures, influencing how universes can evolve over time. While still in its developmental stages, brain cosmology stands as a bridge between established theories and new concepts about the cosmos. Its innovative approach encourages scientists to explore how the universe might be interconnected with other dimensions and realities. This ongoing research not only enriches our understanding of cosmic origins, but also paints a broader picture of existence beyond the confines of our perceived universe. Quantum fluctuations are tiny, random changes in energy that occur in what we call the quantum vacuum. While this concept may seem abstract, it plays a pivotal role in our understanding of the early universe. Before the Big Bang, the universe as we know it today did not exist. However, quantum mechanics suggests that even in this vacuum state, energy is never perfectly zero. There are always fluctuations. These fluctuations represent a kind of background noise, an energetic fabric that lays the groundwork for everything that follows. As scientists explore the universe's origins, they consider theories that propose our universe emerged from these very fluctuations. The idea is that, from this seemingly empty vacuum, regions with slightly greater energy density could expand rapidly, potentially leading to the event we recognize as the Big Bang. This expansion would not only set the stage for the emergence of our universe, but could also explain the uniformity and distribution of matter that we observe today. Moreover, these fluctuations are intricately linked to cosmic inflation, a theory that posits a rapid expansion of the universe just after the Big Bang. During this inflationary period, tiny quantum fluctuations can be stretched to cosmic scales, leaving imprints that are detectable in the cosmic microwave background radiation. This radiation, which is the afterglow of the Big Bang, carries information about those fluctuations and consequently the conditions of the early universe. quantum fluctuations offer a window into a realm of existence that predates the conventional timeline of our universe. By studying these phenomena, scientists not only gain insights into how our universe might have begun, but also uncover fundamental truths about the nature of reality itself. Each discovery about these fluctuations leads us closer to unraveling the mysteries of the time before time, where laws of physics as we understand them were perhaps very different from what we witness today. The concept of energy levels plays a crucial role when exploring pre-Big Bang scenarios, especially in the realm of cosmology and quantum physics. Before the universe as we know it came into existence with the Big Bang, theorists propose various conditions that might have existed. These conditions can often be understood through the language of energy levels. In quantum mechanics, energy levels refer to the fixed amounts of energy that a system, such as an atom or a subatomic particle, can have. In the context of the universe's origin, one intriguing hypothesis suggests that our universe may have started from a state of extremely high energy, possibly involving a quantum vacuum. This vacuum state, despite its name, is not empty. It is characterized by fluctuating energy levels, a phenomenon that can give rise to virtual particles through spontaneous fluctuations. As the universe expanded, these energy levels could have changed, leading to the creation of the matter and energy that constitute our universe. Understanding these energy levels also aids scientists in visualizing the transitions that may have taken place. For example, during the very early moments of the universe, the conditions could have allowed for diverse energy states to coexist, potentially resulting in the rapid inflation that is theorized to have occurred. As the energies decreased, the universe cooled, leading to the formation of fundamental particles and eventually atoms, which laid the groundwork for stars, galaxies, and planets. Moreover, the significance of energy levels extends to the quest for a unified theory of physics. The exploration of energy states can help bridge the gap between general relativity, which governs large-scale cosmic events, and quantum mechanics, which describes the subatomic world. Insights gleaned from these investigations may not only illuminate the pre-Big Bang scenario, but also offer clues about the underlying fabric of the universe, challenging our understanding of time, space, and existence itself. Theories of energetic events and fluctuations are reshaping our understanding of the universe's inception. Traditionally, the prevailing view of cosmic commencement centered around the Big Bang, a singular event marking the beginning of time and space. This notion suggests a clear starting point, leading to the formation of galaxies, stars, and planets. However, new frameworks challenge this linear perspective, proposing that the universe may not have a singular origin, but rather a series of energetic events that have driven cosmic evolution. One of the key ideas in this emerging understanding is the concept of cosmic inflation. This theorizes that shortly after the Big Bang, the universe underwent an exponential expansion, causing various fluctuations in energy density. These fluctuations didn't merely act as a prelude to the formation of structures in the universe, they became integral to understanding how the cosmos evolved over time. Instead of a clean beginning, researchers are now considering a realm where energy states fluctuate, leading to a more complex narrative of cosmic development. Additionally, models involving quantum mechanics introduce a fascinating dimension. Quantum fluctuations could mean that even nothingness is teeming with energy, potentially hinting at alternate mechanisms of cosmic birth. Such frameworks allow for the possibility that the universe has experienced multiple cycles of creation and destruction, presenting an infinitely rich tapestry of existence rather than a singular outset. As scientists continue to unravel these energetic theories, they challenge us to rethink our place in the cosmos. Rather than a simple beginning, the universe may be characterized by a dynamic interplay of forces that exhibit perpetual evolution. Our exploration into these energetic fluctuations invites us to reconsider what we know about cosmic beginnings and how the universe we inhabit may be far more intricate than we ever imagined. The concept of alternate dimensions offers an intriguing perspective on the universe before the Big Bang. Traditional cosmology posits that the Big Bang marks the beginning of our universe, including space and time as we know them. However, theories concerning alternate dimensions suggest that there might be more to the story. They propose that our universe could be just one of many within a larger multiverse, where each universe is potentially governed by different physical laws. These theories often draw upon ideas from string theory, which introduces the existence of additional spatial dimensions beyond the three we experience daily. In this framework, the universe prior to the Big Bang may have existed in a higher dimensional space. This raises the possibility that the Big Bang was not the beginning of everything, but rather a transition point, perhaps a burst of energy sparked by the interaction or collision of different dimensions or universes. Such events could release immense amounts of energy and create the conditions necessary for our universe to emerge. Furthermore, this multiverse perspective allows for the idea that different universes may have unique histories or physical constants, shaping fundamentally different realities. Some models suggest that the properties we observe in our universe could be the result of random fluctuations in a vast array of alternate universes, each going through their own Big Bang processes. This randomness could explain certain constants, like the strength of gravity or the mass of fundamental particles, as being selected from a range of possibilities occurring in a broader dimensional framework. The notion of alternate dimensions provides a fascinating lens through which we can explore the pre-Big Bang universe. It shifts the focus from a singular origin to a more expansive view of existence, suggesting that our universe is part of a complex web of realities, each with their own unique characteristics and histories, offering endless avenues for scientific inquiry and discovery. The notion of extra dimensions beyond our familiar three-dimensional space plus time opens up intriguing possibilities for understanding the conditions and events that might have unfolded prior to the Big Bang. According to theories such as string theory, which proposes that fundamental particles are actually tiny, vibrating strings, these extra dimensions provide additional framework to unify the forces of nature. The existence of such dimensions could imply a landscape in which our universe is just one of many, potentially arising from the interactions and configurations of these extra dimensions. If extra dimensions are indeed part of our reality, they could reshape our understanding of the universe's earliest moments. Before the Big Bang, the traditional view suggests a singularity, a point where space and time came into existence as we know them. However, the introduction of extra dimensions could suggest a more complex pre-Big Bang scenario where space itself may have been structured differently. These dimensions could harbor physics that allows for various states of matter and energy, leading to a richer tapestry of events that paved the way for our universe. Furthermore, the dynamics between different dimensions might have set the stage for the Big Bang itself. In some models, the collisions or interactions between these dimensions could trigger the expansion of our universe. This process could have resulted in the violent release of energy that initiated the rapid expansion known as inflation, a crucial phase that smoothed out the irregularities in the early universe, shaping the cosmos we observe today. Finally, while we currently lack concrete evidence to confirm the existence of extra dimensions, their implications are profound. They invite us to reconsider the very nature of reality and the origins of our universe. Understanding what existed before the Big Bang could fundamentally alter our grasp of existence, revealing a realm that is both mysterious and extraordinary. This potential rewriting of cosmic history continues to spur physicists and cosmologists to explore these intriguing concepts further, fueling the quest for a deeper understanding of our universe. Physicists often turn to theories of higher dimensions to explain complex phenomena in the cosmos. In our familiar three dimensions, we can easily visualize length, width, and height. However, when it comes to theories like string theory or M theory, additional dimensions become essential for a deeper understanding of the universe. In these frameworks, the total number of dimensions can increase to 10 or even 11. These extra dimensions are believed to be compactified or hidden, meaning they are curled up so tightly that we cannot see them with our eyes or even detect them with our current technology. One primary purpose for these higher dimensions is to unify the fundamental forces of nature, such as gravity and electromagnetism. When physicists model realities that involve these extra dimensions, they often use mathematical equations that describe how particles and forces interact. This allows for the exploration of the fundamental aspects of matter and energy in ways that traditional theories cannot account for. For example, in string theory, particles are viewed as tiny vibrating strings, and the frequency of their vibrations determines the type of particle they represent. To visualize these higher dimensions, scientists sometimes employ analogies. One common analogy is that of a garden hose. From a distance, the hose appears one-dimensional, but when inspected closely, its surface reveals a two-dimensional texture. In a similar vein, higher dimensions could be compact in a way that they are not immediately perceptible in our three-dimensional world. This modeling helps scientists make predictions about the behavior of particles at high energies, particularly in environments like those found in outer space or in the early universe. While the concept of higher dimensions can be perplexing, it opens new avenues for understanding the cosmos. Experiments, such as those conducted at particle accelerators, seek evidence for the existence of these dimensions, and advances in cosmology continue to provide insights that align with these theoretical frameworks. The pursuit of these higher dimensional models is a testament to humanity's enduring quest to uncover the underlying fabric of reality. To grasp the implications of dark matter and dark energy on our understanding of pre-Big Bang conditions, we must first explore their enigmatic nature. Dark matter, an invisible substance making up about 27% of the universe, does not emit, absorb, or reflect light. It is inferred from gravitational effects on visible matter, such as galaxies. Dark energy, on the other hand, comprises roughly 73% of the universe and is thought to be responsible for the accelerated expansion we observe today. Understanding these two components not only offers insight into the universe's structure, but also invites us to ponder what existed before the birth of the cosmos. Research into dark matter suggests it plays a crucial role in holding galaxies together, providing a scaffolding of mass that influences the formation and evolution of cosmic structures. This evidence hints at the existence of physical processes that occurred before the Big Bang, potentially allowing scientists to work backward through time. The gravitational interactions caused by dark matter may have set the stage for the conditions that led to the Big Bang, raising questions about whether it was always a part of the cosmos or emerged from a more fundamental state. Dark energy adds another layer of complexity to this puzzle. The uniformity of dark energy across the cosmos could imply that it has been a consistent force throughout the universe's history, possibly influencing or even shaping the conditions that preceded the Big Bang itself. This leads to intriguing hypotheses about the energy dynamics of the universe, including the possibility that the expansion we observe could be a remnant effect from the very early universe, shedding light on a transitional phase that might have existed prior to the Big Bang. Together, dark matter and dark energy open the door to conversations about the universe's origin, urging us to reconsider our existing models and theories. They hint at a cosmic landscape where fundamental processes transcend our current understanding of time and space, encouraging researchers to explore scenarios beyond the conventional Big Bang model. As we delve deeper into these mysteries, we inch closer to unraveling the puzzle of what may have existed just before our universe began its expansion, transforming our comprehension of everything that surrounds us. The mysteries of dark matter and dark energy have intrigued scientists for many years, particularly when considering the conditions of the universe prior to the Big Bang. Current research is delving into theoretical frameworks and models that may help us understand these cosmic components even before the universe's explosive beginning. Notably, astrophysicists are exploring the concept of pre-Big Bang scenarios, where the properties of dark matter and dark energy might play critical roles in shaping the universe's evolution. One area of exploration involves string theory, which posits that the fundamental constituents of the universe are not point-like particles, but rather tiny, vibrating strings. String theorists are investigating how dark matter could manifest in these scenarios, potentially as remnants of a pre-Big Bang state. This approach offers fascinating implications, suggesting that dark matter might have been involved in cosmic inflation, the rapid expansion thought to have occurred just after the Big Bang. Another line of research focuses on simulations and models that account for dark energy in understanding the expansion of the universe. Scientists are examining how the effects of dark energy could alter the fabric of spacetime and influence structures before the Big Bang. Through sophisticated modeling, researchers are attempting to simulate different cosmic conditions and see if these models can produce consistent outcomes with our current understanding of cosmology. Moreover, observational studies employing advanced telescopes are seeking traces of primordial signals that might hint at how dark matter and energy behaved before the Big Bang. By studying cosmic microwave background radiation and gravitational waves, scientists hope to uncover patterns or anomalies that may provide clues. While we still have much to learn, the pursuit of understanding dark matter and dark energy is revealing profound questions that bridge the gap between the beginning of the universe and its potential predecessors. The elusive nature of cosmic components, such as dark matter and dark energy, significantly influences our understanding of the universe's origins. These mysterious entities make up roughly 95% of the cosmos, yet they remain undetected through conventional means. Scientists infer their existence from the gravitational effects they exert on visible matter, like galaxies and clusters. This ambiguity raises questions about the fundamental makeup of the universe and challenges our existing models. When we consider the origins of the universe, particularly the Big Bang theory, the absence of direct evidence for dark matter and dark energy complicates our understanding. These components play crucial roles in cosmic evolution. For instance, dark matter is believed to act as a scaffolding that holds galaxies together, while dark energy is thought to drive the accelerated expansion of the universe. Without a clear picture of these factors, we are left with gaps in our theories about how the universe formed and evolved. Moreover, the quest to uncover the properties of dark matter and dark energy has sparked new scientific inquiries and methods. Researchers are developing sophisticated experiments and instruments to observe the universe in different wavelengths and conditions. These efforts not only enrich our understanding of cosmic components, but they also challenge our fundamental notions of physics, potentially leading to groundbreaking discoveries about the universe's inception. The elusive nature of these cosmic components serves as both a hurdle and a catalyst in our quest for knowledge. As we strive to uncover their secrets, we inch closer to a more comprehensive narrative about the birth and evolution of the universe, one that could redefine our understanding of existence itself. Cosmic anomalies serve as crucial pieces of the cosmic puzzle, offering insights into the conditions that existed before the Big Bang. These anomalies, which include irregularities in the cosmic microwave background radiation, unexpected distributions of galaxies, and variations in dark matter, challenge our understanding of the universe's infancy. They can provide clues about the physical forces and processes that might have shaped our universe prior to its explosive origin. One prominent example of a cosmic anomaly is the way the cosmic microwave background radiation is not perfectly uniform. This radiation is the afterglow of the Big Bang, and slight fluctuations in temperature indicate the uneven distribution of matter in the early universe. These variations suggest that, even in its earliest moments, the universe experienced chaotic dynamics that could have been influenced by conditions prior to the Big Bang itself. Some theories propose that these irregularities may be a remnant of a larger structure or a multiverse, hinting at broader cosmic contexts. Additionally, the distribution of galaxies points to anomalies that could inform our comprehension of cosmic evolution. Observations suggest that galaxies are not randomly spread across the universe, but rather are grouped in surprising patterns. These groupings raise questions about the underlying forces at work, hinting at gravitational interactions shaped by the universe's conditions before the Big Bang. Such patterns could imply that the universe had a complex pre-existing structure before its expansion began. The exploration of cosmic anomalies is not merely a scientific endeavor. It invites us to ponder the fundamental nature of reality. As researchers continue to study these mysteries, they may uncover insights that reshape our understanding of cosmology. The pursuit of knowledge about what came before the Big Bang challenges our intellect and imagination, emphasizing that the universe is a far more intricate place than it often appears. The universe is filled with mysteries that tend to stretch our understanding of traditional cosmological models. Unexplained astrophysical phenomena such as dark matter, dark energy, and the accelerating expansion of the universe can either challenge our existing theories or provide new avenues for refinement. These phenomena often provoke pivotal questions that force astronomers and physicists to rethink the underlying principles of how the cosmos operates. For instance, dark matter, which makes up about 27% of the universe, does not emit, absorb, or reflect light, making it nearly impossible to detect directly. Its existence is inferred from gravitational effects on visible matter and cosmic microwave background radiation. Traditional models of gravity struggle to explain these observations without invoking dark matter. The need to account for such a component illustrates the flexibility of cosmology as a science, whereby modifications to existing theories are necessary to better reflect newly gathered data. Similarly, dark energy, constituting approximately 70% of the universe, is believed to drive the observed acceleration of cosmic expansion. This phenomenon was a shock to astronomers who expected the expansion to slow due to gravitational attraction. The introduction of dark energy forced scientists to dynamically adjust their models of the universe's fate and structure. Understanding dark energy remains one of the most significant challenges in modern cosmology, as it pushes the boundaries of our knowledge about fundamental physics. As researchers continue to uncover these unexplained phenomena, they not only test existing cosmological models, but also spark the development of new theories. Each discovery provides a unique opportunity to deepen our understanding of the universe and our place within it, inviting a continual journey toward not just answering questions, but also appreciating the awe of the cosmos. Intriguingly, just when we think we have the universe figured out, new mysteries emerge, reminding us that the cosmos is as enigmatic as it is beautiful. When scientists encounter anomalies in data while studying the universe's origins, they approach these puzzling observations with a systematic and inquisitive mindset. Anomalies often indicate that there may be something unexpected at play, challenging existing theories and prompting researchers to delve deeper. Rather than disregarding these irregularities, scientists see them as opportunities for discovery, often leading to new insights that can reshape our understanding of cosmic phenomena. The first step in addressing anomalies involves careful verification. Researchers meticulously check the data for errors, considering the possibility of instrument malfunctions or human mistakes in data collection. This rigorous scrutiny ensures that what looks like an anomaly isn't simply an artifact of the data collection process. Only once they are confident in the integrity of the data do scientists begin to explore possible explanations for the unusual findings. Once verified, scientists may develop hypotheses that account for the anomaly. These hypotheses can range from minor adjustments to existing theories to proposing entirely new ideas. For instance, if an anomaly suggests unexpected cosmic behavior, researchers might consider alternative theories regarding dark matter or the expansion rate of the universe. Each hypothesis undergoes scrutiny, being tested against both the existing body of knowledge and new observations. Ultimately, the journey of inquiry continues. Should the anomaly withstand scrutiny and yield compelling evidence for a new understanding, it can lead to paradigm shifts in cosmology. History shows us that many key discoveries, from the existence of dark matter to the mysteries of cosmic microwave background radiation, stem from such unexpected findings. This ongoing process of questioning, testing, and refining reflects the dynamic nature of science, reminding us that our understanding of the universe is always a work in progress. Cosmic recycling is a fascinating concept that refers to the processes of birth, evolution, and eventual death of stars, galaxies, and other celestial bodies. This cycle plays a crucial role in the universe's dynamic nature, where matter and energy continuously change form. At the heart of cosmic recycling is the idea that after stars exhaust their nuclear fuel, they do not simply vanish. Instead, they can explode in dramatic events known as supernovae, scattering elements like carbon, oxygen, and iron into space. This debris eventually coalesces to form new stars, planets, and even life. In this way, the universe perpetually creates and reuses materials, much like a natural recycling system. When we explore what might have existed before the Big Bang, cosmic recycling offers some intriguing insights. Some cosmological models propose that the universe undergoes infinite cycles of expansion and contraction. This theory is known as the Cyclic model, suggesting that the universe may have collapsed and then re-expanded multiple times. Each cycle could potentially recycle matter and energy, leading to a new Big Bang followed by a subsequent contraction. In this scenario, the remnants of past universes would contribute to the materials that shaped our current cosmos. Moreover, this idea challenges the notion of a singular beginning. Instead of viewing the Big Bang as the start of everything, cosmic recycling and cyclic models invite us to consider an ongoing process that might predate what we think of as the origin of our universe. This perspective opens the door to various theories, including the possibility that the universe is eternal, continuously evolving through countless transformations. Interestingly, recent studies in cosmology look into how dark matter and energy, which make up most of the universe, could also play roles in these recycling processes. Understanding cosmic recycling not only enriches our knowledge of the universe's life cycle, but also stimulates curiosity about the very fabric of reality and the underlying laws governing the cosmos. As we delve deeper into these mysteries, we find that the universe is not just a static entity, but a vibrant, ever-changing tapestry woven from the remnants of its own history. Cosmic recycling models offer a fascinating perspective on the life cycle of the universe, where matter and energy continually transform over astronomical timescales. At their core, these models suggest that the universe is not a one-time event, but rather a dynamic system where stars die, and their remnants give rise to new celestial bodies. This idea aligns somewhat with cyclical theories of the universe, which posit that the cosmos undergoes repeated cycles of expansion and contraction. Such a model envisions the universe collapsing back on itself before rebirthing anew, merging the concept of recycling with an eternal rhythm of creation and destruction. When we consider how cosmic recycling interacts with multiverse theories, an intriguing dialogue emerges. Multiverse theories propose the existence of multiple, perhaps infinite universes, each with its own distinct qualities and physical laws. In this context, cosmic recycling might be seen not just within a single universe, but across a vast array of universes. Each universe might recycle matter and energy in unique ways, leading to diverse structures and outcomes throughout the multiverse. This suggests a rich tapestry of interactions not just within our universe, but across the broader cosmic landscape. The interplay between these theories raises profound questions about the nature of existence. If our universe is just one among many, cosmic recycling could take on extraordinary dimensions, as the remnants of one universe might influence another in ways we have yet to comprehend. Imagine a universe where the byproducts of cosmic recycling lead to entirely new laws of physics, giving rise to exotic particles or phenomena that we cannot even begin to envision within our current understanding. This convergence of ideas offers a thrilling glimpse into the possibilities that lie in theoretical astrophysics. By exploring how cosmic recycling, cyclical theories, and multiverse concepts interrelate, scientists and cosmologists can delve deeper into the overarching question of how everything came to be and how it continues to evolve. It's a testament to the creativity of the universe itself and continues to inspire a quest for knowledge that could redefine our understanding of reality. Cosmic recycling theories present an intriguing vision of the universe's future, highlighting the dynamic interplay of stellar formation, evolution, and death. These theories propose that as stars live and die, their materials, the hydrogen, carbon, and other elements forged in their cores, are expelled back into space. This cosmic debris serves as the building blocks for new stars, planets, and potentially life itself. The result is a continuous cycle of birth and rebirth, often described as a cosmic recycling system. As the universe ages, predictions based on these theories suggest that the rate of star formation will change. Initially, stars are created from the vast clouds of gas and dust scattered throughout galaxies. Over billions of years, as these clouds are recycled through supernovae and stellar winds, the gas becomes enriched with heavier elements. This means that newer generations of stars will be different from their predecessors, potentially leading to a universe filled with complex systems capable of supporting diverse forms of life. However, cosmic recycling also has implications for the ultimate fate of the universe. As the universe continues to expand, some theories posit that stars will eventually run out of material to recycle. This could lead to a scenario known as the cold, dark universe, where stellar formation ceases altogether. In this future vision, most stars will have burned out, leaving behind white dwarfs, neutron stars, and black holes. Eventually, these remnants may also fade away, leading to a universe characterized by a slow and steady decline in energy. It becomes a vast, dark expanse populated by dead stars and remnants of their once vibrant lives. The interplay of creation and destruction, so dynamic in the universe's early years, may fade to a quiet stillness, resulting in a cosmos where the activities of the past echo only in the remnants scattered across the void. This cycle of recycling gives us not just a glimpse of our universe's past, but also of its future trajectory, urging us to ponder its ultimate destiny. The no-boundary proposal is an intriguing concept put forth by physicist Stephen Hawking and his collaborator James Hartle. This idea attempts to describe the conditions of the universe at its very inception, suggesting a fascinating framework that challenges traditional notions of a definitive starting point. Instead of envisioning the universe as having a specific boundary or edge, the no-boundary proposal suggests that the universe is finite but without boundaries, much like the surface of a sphere. To understand this idea, imagine the Earth. While the Earth's surface is finite in area, it does not have any edges or boundaries where it simply drops off. In a similar way, Hawking and Hartle propose that the universe can be thought of as existing in a state that does not require a singular point of origin. Prior to the Big Bang, time as we know it ceases to function in the familiar manner, leading to a model where time and space are interwoven into what is called a quantum geometry. This geometry doesn't necessitate a distinct moment of creation, but instead represents a smooth transition from an imaginary time to real time. Within this framework, before the universe emerged, it could be described as having an amplitude for many different configurations, each representing possible states of existence. The no-boundary condition signifies that the universe is not only emerging from this quantum potential, but that all the laws of physics as we know them also converge in this boundaryless beginning. Essentially, the state before the universe is not marked by nothingness. Instead, it embodies a rich tapestry of possibilities in a realm that defies our conventional understanding of before or after. This conceptualization opens up new avenues for understanding the fundamental nature of reality. It challenges scientists and cosmologists to think beyond a linear timeline and examine how the universe's beginnings can inform our current understanding of its evolution. By contemplating a universe without boundaries, we not only delve into the mysteries of its formation, but also raise questions about the nature of existence itself, endlessly captivating the imagination and curiosity of humanity. The no-boundary proposal, primarily associated with physicist Stephen Hawking and cosmologist James Hartle, presents a fascinating perspective on the origins of the universe. This concept suggests that the universe doesn't have any boundaries in time or space, likening its beginning to a sort of smooth and rounded shape, similar to the surface of a sphere. The idea seeks to address what happened at the very first moments of the universe's existence, challenging traditional notions of a singular starting point. One key scientific argument supporting the no-boundary proposal is its reliance on quantum mechanics. In quantum theory, different potential states can exist simultaneously, and this proposal incorporates quantum fluctuations as the seeds for the universe's expansion. According to this view, rather than starting from a singularity, a point of infinite density, the universe emerges from a quantum state with no clear boundary. This interpretation helps avoid some of the paradoxes associated with singularity-based models, providing a smoother transition from non-existence to existence. Critics of the no-boundary proposal raise concerns about its interpretation and implications. One argument against it centers on the predictability of cosmic events under classical physics, which typically expects clear initial conditions for the universe. Detractors point out that if the universe indeed has no boundaries, it becomes challenging to explain how specific phenomena, such as the cosmic microwave background or the distribution of galaxies, originate and evolve over time. They argue that the properties we observe seem to point to more structured beginnings. Yet the no-boundary proposal remains a vibrant topic in cosmological research, particularly as scientists continue to unravel the complexities of the universe's infancy. Its integration with concepts like cosmic inflation, a rapid expansion of space in the early universe, suggests a new way of understanding how the universe has evolved. As researchers dive deeper into both observational data and theoretical models, the no-boundary proposal stands as a testament to the nuanced and ever-evolving dialogue surrounding cosmic origins, sparking curiosity about how our universe came to be. The no-boundary concept, introduced by renowned physicists Stephen Hawking and James Hartle, presents a revolutionary way to understand the universe's origins. Traditionally, the beginning of time has been a perplexing issue, often linked to singularities. points where known physics breaks down and classical notions of time and space lose their meaning. These singularities raise profound questions. What happened before the Big Bang? What might lie beyond this boundary? The no-boundary proposal offers a unique perspective that challenges these conventional ideas. According to this theory, the early universe does not have boundaries in the way we might imagine. Instead, it suggests that the universe is like a smooth, four-dimensional surface where time itself emerges as a dimension alongside space. You can visualize it as a sphere where, as you approach the South Pole, the concept of time as we understand it vanishes. In this model, there is no distinct beginning point or edge to the universe, effectively sidestepping the traditional beginning of time dilemma that arises with singularities. Another aspect of this model introduces the concept of imaginary time. In simple terms, this means that, at the universe's origins, the time dimension behaves differently from how we experience it today. By transforming real time into imaginary time, the mathematical descriptions soften the harsh realities we associate with singularities. This indicates that instead of an explosive start, the universe may have transitioned smoothly from a timeless state into the familiar expanding cosmos we observe now. This overarching framework provides a fresh narrative for understanding the early universe. Rather than picturing time as a linear path originating from a precise moment, the no-boundary idea allows us to consider a more complex, nuanced beginning. It invites us to rethink our definitions of time and space in relation to the cosmos, reinforcing the notion that the universe could, indeed may, exist without a definitive starting point, opening doors to fascinating implications for the nature of reality itself. Exploring the pre-Big Bang universe poses a multitude of challenges for researchers, primarily due to the fundamental nature of how the cosmos began. First and foremost, the concept of time as we understand it may not apply to the universe before the Big Bang. Traditional physics struggles with the very notion of a time before time, complicating our ability to frame and comprehend events that may have occurred under different physical laws than those we are familiar with today. Moreover, our current understanding of the universe is rooted in observation, which relies on light and other forms of radiation traveling through space. However, any events or conditions that existed before the Big Bang are obscured by the cosmic microwave background radiation. This ancient glow, considered the afterglow of the Big Bang, envelops any earlier moments in a thick fog of energy. As such, researchers cannot directly observe what transpired before this critical moment, leading to a reliance on theoretical models that remain untested against empirical data. Theoretical frameworks like quantum gravity and string theory attempt to bridge the gap between the very small scales of particles and the cosmic scales of the universe. Yet these theories remain speculative, lacking the robust verification that typically strengthens scientific concepts. The challenge lies not only in formulating mathematical models, but also in finding ways to validate those models against observable phenomena, which is crucial in any scientific inquiry. Lastly, there is the inherent debate surrounding the interpretation of evidence and the implications it carries. Ideas about a cyclical universe, multiverses, or quantum fluctuations as precursors to the Big Bang lead to rich discussions but also considerable uncertainty. These narratives raise profound questions about the nature of reality itself and challenge our understanding of physics. In light of all these complexities, researchers continue to push the boundaries of cosmology, eager to unravel the mysteries of the cosmos that stretch back to its very origins, still veiled in enigma and allure. The quest to understand the origins of the universe has fascinated scientists for centuries, yet many questions remain unanswered. To tackle these profound mysteries, researchers are employing both observational methods and theoretical models that encompass various fields of physics, astronomy, and cosmology. One of the most promising approaches involves studying cosmic background radiation, the remnant heat from the Big Bang. This radiation serves as a snapshot of the universe when it was just a fraction of a second old, offering clues about its initial conditions and the forces at play. In addition to observing cosmic background radiation, scientists are utilizing advanced telescopes and satellite technology to explore distant galaxies and cosmic phenomena. By analyzing light from distant stars and galaxies, researchers can track how the universe has evolved over billions of years. Projects like the James Webb Space Telescope are set to revolutionize our understanding by providing deeper and clearer views of the cosmos, focusing on the formation of the first stars and galaxies and how structures in the universe developed over time. Another innovative strategy involves particle physics, particularly experiments conducted at facilities like the Large Hadron Collider. By smashing particles together at incredibly high energies, scientists hope to replicate conditions similar to those present in the early universe. These experiments could provide insights into fundamental forces and particles, potentially offering a window into what might have occurred just after the Big Bang and how those conditions set the stage for everything that followed. Moreover, theoretical physicists are exploring novel concepts such as string theory and quantum gravity. These frameworks aim to reconcile the principles of quantum mechanics with general relativity, possibly leading to a deeper understanding of the fabric of spacetime itself. As scientists continue to push the boundaries of knowledge through observations and theoretical advancements, they inch closer to answering the profound questions about our universal origins, unraveling the intricate tapestry that connects us all to the cosmos. As we look to the future, several emerging technologies hold the promise of unveiling new insights into the universe's beginnings. One of the most significant advancements is the field of gravitational wave astronomy. Following the groundbreaking detections of gravitational waves in 2015, scientists have begun to refine their abilities to capture these ripples in spacetime. These waves originate from cataclysmic events, such as colliding black holes or neutron stars. By studying these phenomena, researchers can glean information about the universe shortly after the Big Bang, offering a new lens through which to view cosmic history. In addition to gravitational waves, next-generation telescopes are set to revolutionize our understanding of the cosmos. The James Webb Space Telescope, for example, is designed to observe the universe in infrared wavelengths, which will allow it to penetrate dust clouds and observe the first galaxies formed after the Big Bang. This telescope, launching specific observations of distant celestial objects, could reveal critical details about the formation and evolution of the universe. As more advanced telescopes become operational, they will enable astronomers to address enduring questions about dark matter and dark energy, two mysterious components that shape much of our cosmic landscape. Another exciting technological frontier lies in the realm of particle physics, particularly with the upgrades to particle accelerators like the Large Hadron Collider. These facilities recreate high-energy conditions similar to those just moments after the Big Bang. By colliding particles at unprecedented speeds, scientists can explore fundamental forces and particles that were present during the early universe. These experiments could deepen our understanding of the conditions that led to the creation of matter and the universe as we know it, potentially answering questions that have puzzled cosmologists for decades. Moreover, advancements in artificial intelligence and machine learning are transforming data analysis in the field of cosmology. As observatories generate vast amounts of data, these tools can help identify patterns and anomalies that human observers might overlook. This means that we could discover previously unseen cosmic structures or events, providing fresh perspectives on the universe's origins. With these innovative technologies at our disposal, the mysteries of the universe's beginnings may soon be illuminated, offering us a deeper connection to our place in the cosmos. When it comes to exploring pre-Big Bang theories, researchers face the intriguing challenge of sifting through a landscape of speculative ideas. The focus often starts with the questions that arise from existing evidence and our current understanding of the universe. Theories that offer potential to provide new insights into cosmic history or explain anomalies in observational data tend to rise to the forefront. This approach not only encourages a rigorous examination of foundational concepts, but also allows researchers to build upon established frameworks. Scientists are also keenly interested in theoretical models that align with well-supported areas of physics, such as quantum gravity or string theory. These frameworks propose mechanisms that could govern the conditions before the Big Bang. Researchers prioritize these theories based on how well they can integrate with known physics, while simultaneously filling gaps in our knowledge about the origins of the universe. The interplay between abstraction and empirical data is crucial, as compelling theories must hold up under scrutiny from both theoretical predictions and observational evidence. Collaborative discussions within the scientific community play a significant role in prioritization. Conferences and workshops serve as platforms for exchanging ideas, where researchers can critique and refine each other's theories. Popularity is not merely a matter of reputation, it hinges on the feasibility of experimental validation. If a theory can potentially be tested through future observations or technological advancements, it stands a better chance of gaining traction. Ultimately, the prioritization of pre-Big Bang theories is a dynamic process, constantly evolving as new data emerges or as existing theories are challenged. Scientists remain committed to curiosity and rigor, searching for answers that could illuminate the mystery of the universe's true beginnings. This journey into the unknown reflects not just a desire for knowledge, but an intrinsic human impulse to understand our place in the cosmos. Advancements in theoretical physics are revolutionizing our understanding of the universe, particularly the enigmatic period before the Big Bang. Traditionally, the Big Bang has been viewed as the absolute beginning of time and space, a monumental event that marked the birth of our cosmos. However, cutting-edge theories are leading scientists to reconsider this notion, suggesting that the universe may have existed in some form even prior to this explosive beginning. One fascinating idea comes from the realm of quantum gravity, which seeks to merge the principles of quantum mechanics with general relativity. Some physicists propose scenarios in which our universe undergoes cyclical phases, suggesting that it could have a past extending infinitely. In these models, the universe experiences cycles of expansion and contraction, hinting that the Big Bang may have been merely the latest transition rather than an undeniable starting point. Another intriguing avenue of exploration is string theory, which posits that the fundamental building blocks of the universe are one-dimensional strings rather than point-like particles. This theory opens up the possibility of dimensions beyond the familiar three, creating complex landscapes of physics that could accommodate pre-Big Bang conditions. Such a framework may allow for alternative mechanisms of cosmic creation, inviting us to think of the universe as a rich tapestry woven over vast epochs, with intricate interconnections that challenge our simple linear view of time. As researchers probe deeper into these theoretical realms, they not only expand our grasp of cosmic history, but also push the boundaries of human imagination. By challenging foundational concepts of time and existence, these advancements may reveal a much more intricate and unified cosmos than we had ever thought possible. The implications are profound, urging us to rethink not just where the universe came from, but where it might be headed next, and how our understanding of reality itself is continually evolving. Theoretical breakthroughs are pivotal in reshaping our understanding of the cosmos and its origins, acting like fresh lenses through which we can view the vastness of the universe. Throughout history, significant advances, ranging from Newton's laws of motion to Einstein's theory of relativity, have altered our perspective on how celestial bodies interact and how the universe itself behaves. Each new theory leads to further questions, stimulating research and exploration and enhancing our grasp of complicated phenomena. For example, the introduction of concepts like dark matter and dark energy has fundamentally redefined our view on the composition of the universe. While visible matter makes up only a fraction of the cosmos, these theoretical constructs suggest that nearly 95% of the universe's energy density is interwoven with invisible components. This unexpected revelation challenges physicists and astronomers to rethink not only the structure of the universe, but also the fundamental laws governing it. Moreover, new theories often emerge from the fusion of ideas across multiple disciplines. The merger of quantum mechanics and general relativity, for instance, is a hotbed of inquiry aimed at understanding the behavior of matter and energy at both the smallest and largest scales. These cross-disciplinary breakthroughs invite researchers to craft comprehensive frameworks that can account for everything from the behavior of subatomic particles to the dynamics of galaxies, potentially leading to a unifying theory that captures the essence of the cosmos. As each new breakthrough arises, it is accompanied by a multitude of questions ripe for exploration. These unanswered questions can drive technological innovation, requiring new tools and methods for observation and analysis. As we stand on the shoulders of these theoretical advancements, The quest to decode the mysteries surrounding the origins of the universe continues, inviting both experts and the curious public to ponder our place in the grand tapestry of existence.